Welcome, friends. I'm so glad you're here, whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion. You found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quantum foam that underlies all reality, where even empty space reveals itself as anything but vacant. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The vacuum between stars appears empty to casual observation, a vast nothingness punctuated only by the occasional drift of cosmic dust or the distant light of dying suns. Astronomers once believed this darkness represented true emptiness, regions of space containing literally nothing at all. They imagined perfect voids stretching across light years, territories where not even the smallest particle dared venture. This vision of cosmic emptiness persisted for centuries, a comforting simplicity that suggested space served merely as a passive container for matter and energy. Yet physicists have discovered that this apparent emptiness seethes with activity at scales so minute they challenge the very meaning of existence itself. In regions of space containing not a single atom, not a whisper of matter, quantum mechanics reveals a bubbling froth of virtual particles that pop into being and vanish again in time frames measured in units smaller than the time it takes light to cross a proton. The quantum vacuum resembles nothing so much as a pot of water approaching boil. Though the metaphor fails to capture the strangeness of what actually occurs, these phantom particles emerge like thoughts surfacing from a dreaming mind, following rules that defy everyday logic yet govern the universe's most fundamental processes. An electron and its antimatter twin, the positron, materialize from pure vacuum for briefer than brief moments before annihilating each other and returning to the nothingness from which they came. The electron carries negative electric charge while the positron carries positive charge, their combined charge totaling exactly zero to satisfy conservation laws. They exist as perfect opposites, mirror images that can exist only together and must vanish together, maintaining the universe's careful accounting even as they violate it temporarily. Photons flicker into existence carrying borrowed energy from the universe's fundamental uncertainty, existing just long enough to interact with their surroundings before dissolving back into potential. Unlike matter particles, photons can emerge from vacuum singly, appearing and disappearing like distant lightning in a summer sky. The entire process unfolds in accordance with Heisenberg's uncertainty principle, which permits the universe to borrow energy from its own future, provided the debt is repaid quickly enough that reality's bookkeeping remains balanced. The mathematics governing these processes emerged from decades of theoretical development as physicists struggled to reconcile quantum mechanics with Einstein's special relativity. The resulting quantum field theory describes particles not as tiny billiard balls, but as excitations in underlying fields that permeate all of space. Empty space becomes the ground state of these fields, their lowest possible energy configuration. Yet even this ground state writhes with zero-point fluctuations that can never be eliminated. Scientists measure this quantum foam through its subtle effects on atoms and light, influences so delicate they remained undetected until the middle of the 20th century. The Casimir effect demonstrates how two metal plates placed impossibly close together in a perfect vacuum experience a measurable attractive force as virtual particles push against them from outside while fewer virtual particles fit in the narrow space between. Dutch physicist Hendrik Casimir predicted this force in 1948 based purely on theoretical calculations. imagining how electromagnetic field fluctuations would behave in confined spaces. It took researchers decades to isolate this whisper-thin influence from other forces, requiring instruments sensitive enough to detect pushes weaker than the weight of a soap bubble. Yet there it remains, as reproducible as sunrise, proof that emptiness itself possesses structure and can exert measurable influence on matter. The foam's influence extends far beyond laboratory curiosities, pervading every aspect of atomic and molecular behavior. Virtual particles contribute to the magnetic properties of electrons, causing tiny deviations from values predicted by simpler theories. They affect how atoms absorb and emit light, shifting spectral lines by amounts detectable only through the most precise measurements. They modify the strength of electromagnetic forces at quantum scales, causing the electric charge of electrons to vary slightly depending on the energy used to probe them. Virtual photons mediate all electromagnetic forces between charged particles, carrying messages between electrons and protons that determine atomic structure. These messenger particles remain strictly virtual, never appearing as real photons that could be detected independently. Yet their exchanges account for every aspect of electromagnetic behavior, from chemical bonding to the operation of electronic devices. Some theories suggest virtual particles might even influence the formation of matter in the early universe, when space itself was compressed to dimensions where quantum effects dominated over classical physics. During the first moments after the Big Bang, virtual particle fluctuations may have been amplified into the density variations that eventually grew into galaxies and stars. The cosmic microwave background radiation bears patterns that some cosmologists interpret as fossilized quantum fluctuations from the vacuum itself. Only the most sensitive instruments can detect these virtual fluctuations directly. Yet they permeate every cubic millimeter of space throughout the observable universe. Their energy density appears vanishingly small, yet when integrated across cosmic volumes, it should produce gravitational effects larger than anything observed. This discrepancy represents one of physics' most profound puzzles, suggesting our understanding remains fundamentally incomplete. Perhaps most mysteriously, nobody knows whether virtual particles actually exist as discrete entities or represent mathematical artifacts of our current theories. They emerge naturally from quantum field theory's equations, arising inevitably when physicists attempt to calculate how real particles interact. The mathematics requires their inclusion to achieve agreement with experimental observations, yet the particles themselves remain forever unobservable in isolation, existing only through their collective effects. The debate continues in academic journals and conference halls, a gentle disagreement over whether the universe's foundation consists of something or nothing at all. Some physicists argue virtual particles represent real processes occurring in space and time, actual entities with definite properties that happen to be undetectable by any conceivable instrument. Others suggest they merely reflect the limitations of human mathematics when describing quantum reality. Useful fictions that enable calculations without corresponding to anything physically real. The irony settles quietly into contemplation. As profound as any meditation on existence itself, the most sophisticated theories of modern physics suggest that perfect emptiness cannot exist. That space itself writhes with invisible activity more complex than the surface of any ocean. The vacuum reveals itself as perhaps the most densely populated place in existence, filled with particles that may or may not actually be there, interacting through forces that shape matter across cosmic distances, while remaining themselves forever hidden from direct observation. Scientists measure effects produced by entities whose existence remains questionable, building technologies based on phenomena that may represent nothing more than useful mathematical illusions. Quantum mechanics works with unprecedented precision, enabling the development of lasers, transistors, and magnetic resonance imaging machines. Yet its foundational concepts remain as mysterious today as they were a century ago. In the end, empty space becomes a meditation on the nature of existence itself, where presence and absence blur into quantum superposition, and the foundation of all matter rests upon a contradiction as delicate as foam. The vacuum holds its secrets quietly, neither confirming nor denying its own reality, content to influence the universe through effects too subtle for certainty, yet too consistent for dismissal. Light moves through space with the constancy of a cosmic heartbeat, its speed unchanging whether it emerges from distant quasars or the screen illuminating these words. For centuries, this consistency suggested light possessed a simple, unified nature that physicists could eventually understand completely. Yet deeper investigation reveals light behaving as both wave and particle simultaneously, a fundamental contradiction that remains unresolved after more than a century of investigation, challenging the very notion that reality must conform to human logic. The wave nature of light manifests in phenomena as commonplace as rainbows and as sophisticated as laser interferometry. Light diffracts around obstacles, creating patterns of brightness and shadow that match the mathematics of waves spreading through water or sound propagating through air. When light passes through narrow slits, it creates interference patterns where waves reinforce and cancel each other, producing alternating bands of illumination and darkness that demonstrate light's ability to interfere with itself. These wave properties enable technologies from radio communication to optical microscopy, all dependent on light's capacity to spread, bend, and combine in ways that only waves can accomplish. Yet light also behaves as discrete particles called photons, packets of electromagnetic energy that arrive at detectors as indivisible units. Photoelectric cells convert light directly into electrical current by absorbing photons one at a time, each photon kicking an electron loose from its atomic bonds with precisely the energy Einstein predicted in his Nobel Prize-winning explanation. Digital cameras capture images by counting photons that strike their sensors, accumulating discrete clicks of energy into the continuous images perceived by human vision. Even the faintest starlight consists of individual photons traveling across cosmic distances, each carrying specific amounts of energy determined by the temperature and composition of its stellar source. The mystery deepens when physicists attempt to observe both natures simultaneously. The famous double-slit experiment demonstrates this puzzle with elegant simplicity. When light passes through two parallel slits onto a detector screen, it creates the interference pattern characteristic of waves, with alternating bright and dark bands showing where light waves reinforce or cancel each other. Yet when detectors monitor which slit each photon passes through, the wave pattern disappears entirely, replaced by two simple bands directly behind each slit, as if individual particles traveled through one slit or the other, but never both simultaneously. The transition between wave and particle behavior depends entirely on the act of measurement itself, as if reality changes its fundamental nature in response to human observation. When no detector monitors the slits, individual photons somehow pass through both slits simultaneously, interfering with themselves to create wave patterns. When detectors attempt to determine each photon's path, the same photons behave as particles, choosing definite trajectories and losing their wave-like properties completely. The change occurs instantly and completely, suggesting that the nature of light itself remains fundamentally uncertain until the moment of measurement forces it to choose a specific form. This wave-particle duality extends beyond light to encompass all quantum entities. Electrons, protons, and even entire atoms exhibit both wave and particle characteristics, depending on how experiments observe them. Matter waves, first predicted by Louis de Broglie, have been demonstrated for particles as large as molecules containing hundreds of atoms. The wavelength of these matter waves decreases with increasing mass and velocity, explaining why everyday objects appear purely particle-like, while microscopic entities display obvious wave behavior. Yet the mathematics suggests that even human beings possess wave-like properties, though with wavelengths so impossibly small that wave effects become utterly negligible at macroscopic scales. Quantum mechanics embraces this contradiction through the concept of complementarity, proposed by Niels Bohr as a fundamental principle governing microscopic reality. According to complementarity, wave and particle descriptions represent equally valid yet mutually exclusive ways of understanding quantum phenomena. The choice of experimental apparatus determines which aspect manifests, but both aspects remain essential for complete understanding. Like viewing a three-dimensional object from different angles, wave and particle perspectives reveal different facets of the same underlying reality, though in this case, the different perspectives appear logically contradictory rather than merely incomplete. The philosophical implications ripple outward like waves from a disturbed pond. If light possesses no definite nature independent of observation, what does this suggest about the reality of unobserved phenomena? Some interpretations propose that quantum entities exist in superposition states, simultaneously exhibiting all possible characteristics until measurement collapses them into definite configurations. Others suggest that wave and particle descriptions merely reflect limitations in human conceptual frameworks, useful approximations to phenomena that transcend classical categories entirely. Modern quantum field theory attempts to resolve the duality by describing both light and matter as excitations in underlying quantum fields that permeate all space. Photons become localized excitations in the electromagnetic field, while electrons represent excitations in the electron field, and so forth. This field perspective unifies wave and particle descriptions under a single mathematical framework, yet it pushes the mystery deeper rather than eliminating it entirely. The fields themselves exhibit wave-like properties, yet their excitations behave as discrete particles, preserving the essential duality at a more fundamental level. The practical applications of wave-particle duality enable much of modern technology, from the photoelectric effect that powers solar cells to the wave interference that enables holography and optical computing. Laser systems depend on light's particle nature for energy quantization and its wave nature for coherence and interference effects. Electron microscopy exploits the wave properties of electrons to achieve resolution beyond the limits of optical instruments, while electron guns in television screens and computer monitors treat electrons as particles following definite trajectories. The same entities that create these technologies continue to challenge fundamental assumptions about the nature of existence itself. Perhaps most remarkably, the wave-particle duality appears to be a permanent feature of physical reality rather than a temporary puzzle awaiting resolution. Decades of theoretical development and experimental refinement have only deepened the mystery, revealing new aspects of the phenomenon without eliminating its fundamental contradictions. Modern quantum mechanics predicts and explains the duality with mathematical precision, yet offers no intuitive picture of how single entities can simultaneously possess contradictory properties. The mathematics works perfectly, while the underlying reality remains as mysterious as ever. The contemplation settles into quiet acceptance of paradox. Light continues to travel through space with perfect consistency, carrying information across cosmic distances and enabling vision, photosynthesis, and the myriad processes that sustain life on Earth. Yet this same light defies every attempt to fit it into logical categories, remaining simultaneously wave and particle, continuous and discrete, spread throughout space and localized at specific points. The mystery persists not as a failure of science, but as a fundamental feature of reality itself, a reminder that the universe operates according to principles more subtle than human intuition can fully grasp. only took over a century for physicists to accept that nature simply doesn't conform to classical logic at quantum scales. The act of measurement transforms quantum reality in ways that challenge every intuitive notion of how the world operates. Before observation. Quantum systems exist in superposition states, simultaneously exhibiting all possible properties with definite probabilities but no definite values. A single photon traveling toward a detector exists in a ghostly combination of all possible paths until the moment it strikes the detector, when the superposition collapses instantly into a single, definite outcome. This measurement problem represents one of quantum mechanics' most profound puzzles, suggesting that reality itself changes in response to conscious observation through mechanisms that remain completely unknown. The mathematics of quantum mechanics describes superposition with elegant precision. Schrödinger's wave equation calculates the probability amplitudes for finding particles in various states, treating each possible outcome as a component in a mathematical superposition. The wave function evolves smoothly and deterministically over time, following laws as precise as those governing planetary motion. Yet the moment any measurement occurs, this smooth evolution gives way to an instantaneous, random collapse that selects one outcome from the infinite possibilities encoded in the superposition. The transition from deterministic evolution to random collapse happens without warning and without any physical mechanism to explain the transformation. Schrödinger himself illustrated the paradox's absurdity through his famous thought experiment involving a cat simultaneously alive and dead. A quantum particle in superposition triggers a mechanism that either releases poison or leaves it contained, depending on whether the particle decays within a specified time interval. According to quantum mechanics, the particle exists in superposition until observed, simultaneously decayed and undecayed. This superposition should extend to the poison mechanism and ultimately to the cat itself, creating a macroscopic object existing in superposition of life and death until someone opens the box to observe the outcome. The thought experiment exposes the uncomfortable boundary between quantum and classical reality. Microscopic particles routinely exist in superposition states that have been verified through countless experiments. Yet macroscopic objects like cats appear definitively alive or dead independent of observation. Somewhere between atomic and everyday scales, quantum superposition gives way to classical definiteness. Yet nobody knows where this boundary lies or what physical processes govern the transition. The cat paradox forces confrontation with questions about consciousness, measurement, and the role of observers in determining reality itself. Real experiments with quantum systems demonstrate superposition's reality at microscopic scales. Individual atoms can be prepared in superposition states where they exist in multiple energy levels simultaneously, occupying orbital configurations that classical physics would consider impossible. These superposed atoms emit light with interference patterns that could only result from the atom interacting with itself across multiple quantum states. Electron spins exist in superposition of pointing both up and down until measurement forces them to choose definite orientations. Even the positions of particles can be superposed, with single electrons detected at multiple locations simultaneously until observation collapses their wave functions into specific coordinates. The collapse of superposition happens instantaneously across any distance, violating Einstein's principle that nothing can travel faster than light. When a measurement determines the spin of one electron in an entangled pair, the partner electron's spin becomes definite immediately, regardless of whether it lies in the same laboratory or on the opposite side of the galaxy. This instantaneous correlation suggests that quantum measurement involves non-local processes that transcend the space-time limitations governing classical physics. Einstein called this spooky action at a distance, expressing his discomfort with quantum mechanics' apparent violation of relativity's fundamental principles. The measurement problem becomes even stranger when considering delayed choice experiments that seem to reach backward through time. Physicists can arrange apparatus so that the decision of whether to measure wave or particle properties occurs after light has already passed through the experimental setup. Yet, the type of measurement chosen affects the behavior that the light exhibited earlier, as if future measurements retroactively determine past reality. These experiments suggest that the act of measurement doesn't simply reveal pre-existing properties, but actively participates in creating the very properties it discovers. Different interpretations of quantum mechanics propose various solutions to the measurement problem, though none has achieved universal acceptance among physicists. The Copenhagen interpretation, developed by Bohr and Heisenberg, treats measurement as a fundamental process that cannot be reduced to more basic physical mechanisms. According to this view, quantum systems remain in superposition until they interact with classical measuring apparatus, at which point the wave function collapses and definite properties emerge. The interpretation works perfectly for practical calculations, but offers no explanation for why or how this collapse occurs. The many worlds interpretation, proposed by Hugh Everett, eliminates wave function collapse by suggesting that all possible measurement outcomes actually occur in parallel universes. When a measurement appears to collapse a superposition, the universe actually branches into multiple copies, one for each possible outcome. The observer experiences only one branch, but all possibilities remain equally real in the broader multiverse. This interpretation preserves quantum mechanics' mathematical consistency while multiplying reality into an infinite collection of parallel worlds, most of which remain forever inaccessible to verification. Hidden variable theories propose that quantum particles possess definite properties at all times, with apparent randomness arising from our ignorance of these hidden characteristics. Local hidden variable theories were definitively ruled out by Bell's theorem and subsequent experiments, but non-local hidden variables remain possible. These theories suggest that particles maintain instantaneous connections across arbitrary distances, sharing information faster than light to coordinate their behavior during measurements. While such theories can reproduce quantum mechanics predictions, they require abandoning locality, one of relativity's most fundamental principles. Objective collapse theories propose that wave function collapse represents a real physical process that occurs spontaneously without requiring conscious observers. According to these theories, superposition states become unstable above certain size or complexity thresholds, causing them to collapse randomly into definite configurations. The collapse rate increases with the number of particles involved, explaining why microscopic systems maintain superposition while macroscopic objects appear classical. These theories require modifications to quantum mechanics' basic equations, adding terms that cause spontaneous localization while preserving all experimentally verified predictions. The role of consciousness in quantum measurement remains one of physics' most contentious questions. Some interpretations suggest that conscious observation plays a fundamental role in collapsing wave functions, making mind an essential component of physical reality. Others argue that any irreversible interaction with the environment constitutes measurement, regardless of whether conscious observers are present. Experiments with automated detectors that record measurements without human observation show the same wave function collapse, suggesting that consciousness itself may be irrelevant to the process. Decoherence theory attempts to explain the emergence of classical behavior from quantum systems without invoking wave function collapse. According to this approach, quantum systems never truly collapse, but become entangled with their environments in ways that make superposition unobservable. The environment acts like a continuous monitoring system, destroying coherence between different components of superposition states. While decoherence explains the appearance of classical behavior, it doesn't solve the fundamental measurement problem. since the combined system of particle plus environment remains in superposition according to quantum mechanics equations. The philosophical implications extend far beyond physics into questions about the nature of reality, consciousness, and knowledge itself. If measurement creates rather than reveals properties, what can be said about the reality of unobserved phenomena? Does the moon exist when nobody looks at it, as Einstein famously asked, or does it exist only in the quantum superposition of all possible moons until astronomical observation collapses it into the specific moon we observe? The questions sound absurd when applied to everyday objects, yet they follow logically from quantum mechanics' most fundamental principles. Modern technology depends on controlled quantum measurements, from the photodetectors in digital cameras to the quantum sensors that enable atomic clocks and gravitational wave detectors. These devices operate by preparing quantum systems in well-defined states and then measuring their evolution with extraordinary precision. The same measurement problem that puzzles theorists enables practical applications that have revolutionized communication, navigation, and scientific observation. The mystery of measurement becomes a tool for exploring deeper mysteries about space, time, and the fundamental structure of reality. Perhaps most remarkably, the measurement problem appears to be getting stranger rather than simpler as experimental techniques improve. Quantum computers manipulate superposition states with increasing sophistication, maintaining coherence across larger numbers of quantum bits and longer time intervals. These systems reveal new aspects of superposition while highlighting the artificial nature of any boundary between quantum and classical behavior. Each advance in quantum control deepens rather than resolves the fundamental questions about measurement and reality. The contemplation of measurement settles into profound uncertainty about the nature of existence itself. Every observation, from reading these words to watching stars twinkle in the night sky, involves quantum measurements that collapse superposition states into definite outcomes. Yet the mechanism behind this collapse remains as mysterious as consciousness itself. Perhaps because consciousness and measurement represent different aspects of the same fundamental process, reality appears to exist in a constant state of becoming, continuously crystallizing from quantum possibility into classical actuality through the mysterious alchemy of observation. The universe measures itself constantly, each interaction between particles constituting a measurement that transforms probability into actuality. Stars form from gravitational collapse that represents a kind of cosmic measurement, concentrating matter from diffuse clouds into definite stellar configurations. Life itself emerges through molecular measurements that extract specific outcomes from quantum possibilities, building complex structures through countless acts of observation and selection. Perhaps measurement represents not an anomaly in physics, but the fundamental process through which reality creates itself moment by moment. Only took a century of investigation to realize that the act of looking might be the most mysterious process in the universe. Every quantum event potentially splits reality into countless parallel universes, each containing different versions of every moment that has ever occurred or ever could occur. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, suggests that the wave function never actually collapses, but continues evolving deterministically across an infinite multiverse where all possible outcomes of every measurement happen simultaneously. In this view, the universe branches continuously like an ever-growing tree, with each quantum interaction spawning new worlds that diverge from each other in ways both subtle and profound. The branching occurs at every scale, from the decay of individual radioactive atoms to the firing of neurons in conscious brains. When a Geiger counter detects radiation from a uranium sample, traditional quantum mechanics describes the probabilistic collapse of the atom's wave function into either decayed or undecayed states. The many worlds interpretation instead proposes that both outcomes occur. creating one universe where the atom decayed and triggered the detector, and another universe where the atom remained intact and the detector stayed silent. Both universes continue existing with equal reality, though observers in each universe remain aware only of their particular branch of the cosmic tree. The mathematics supporting this interpretation follows directly from quantum mechanics' fundamental equations without requiring additional assumptions about wave function collapse. Schrödinger's equation describes the wave function as evolving smoothly and deterministically, never showing any discontinuous jumps or random transitions. The appearance of collapse emerges naturally when conscious observers become entangled with quantum systems, splitting into multiple copies that each experience definite outcomes while remaining unaware of their parallel selves. The interpretation preserves quantum mechanics' mathematical elegance while eliminating its most problematic feature, the mysterious transition from probability to actuality. Each branching event creates worlds that initially differ by only microscopic details, but can diverge dramatically over time through the amplification of quantum differences. A cosmic ray striking DNA during cell division might cause a mutation in one world while leaving the genetic sequence intact in a parallel universe. The mutated cell could eventually lead to cancer in one branch, while the parallel individual remains healthy throughout life. These divergent health outcomes cascade through families, societies, and civilizations, creating worlds where different people exist, different discoveries occur, and different histories unfold from identical starting conditions. The number of parallel worlds increases exponentially with each quantum event, reaching incomprehensibly vast multiplicities within microseconds of the universe's beginning. Every quantum interaction in every atom throughout cosmic history generates new branches, creating a multiverse whose size defies even mathematical description. Some branches differ by single particle positions, while others diverge through completely different evolutionary pathways, technological developments, and cultural trajectories. The totality encompasses every possible variation of physics, chemistry, biology, and consciousness that quantum mechanics permits. Branching occurs continuously throughout space and time, with different regions of the universe splitting independently based on their local quantum events. A radioactive decay in a distant galaxy creates worlds that differ by that single nuclear transition, while quantum processes in nearby laboratories simultaneously generate additional branches through their own measurements and interactions. The multiverse resembles an infinite collection of parallel films playing simultaneously, each differing from its neighbors by quantum details that accumulate into macroscopic differences over time. The interpretation raises profound questions about personal identity and the nature of consciousness across multiple worlds. Every decision influenced by quantum processes in the brain creates branches where different choices occur, generating parallel versions of every conscious being who experience alternative life trajectories. These parallel selves remain equally real, yet forever isolated from each other, unable to communicate across the barriers separating different branches of reality. Each version experiences their particular world as the only reality while remaining unaware of countless alternatives unfolding simultaneously. Some branches contain worlds nearly identical to this one, differing only by the positions of a few subatomic particles in remote regions of space. Others diverge more dramatically, featuring different weather patterns, election outcomes, or scientific discoveries that alter the course of human civilization. Still, other branches explore possibilities where quantum randomness influenced early evolutionary processes, creating worlds with entirely different forms of life or no life at all. The multiverse encompasses every story that quantum mechanics allows, from subtle variations on familiar themes to radically alien narratives beyond human imagination. The apparent randomness of quantum measurements emerges naturally from observers' inability to perceive all branches simultaneously. Each measurement outcome appears random from within any single world, Yet the complete set of outcomes across all worlds follows quantum mechanics' probabilistic predictions exactly. The wave function evolves deterministically through the multiverse, while individual observers experience seemingly random collapses as they become entangled with quantum systems and split into multiple copies. Communication between parallel worlds appears impossible according to current understanding. Since the branches become decoherent through their interactions with environmental degrees of freedom, once worlds split, they evolve independently without influencing each other, creating permanently separate realities that share only their common past before the branching event occurred. This isolation prevents paradoxes that might arise from information transfer between worlds with different histories, maintaining logical consistency within each branch while preserving the overall coherence of the multiverse. The interpretation eliminates several conceptual problems that plague other approaches to quantum mechanics. The measurement problem disappears since wave functions never collapse, only branch into multiple components corresponding to different outcomes. The role of consciousness becomes irrelevant to physical processes, since branching occurs automatically through quantum interactions regardless of whether conscious observers are present. The apparent conflict between quantum mechanics and relativity resolves since no information travels faster than light between measurement events. The correlations arise from shared histories before branching rather than instantaneous communications. Yet many worlds' interpretation creates new puzzles while solving old ones. The vast majority of branches contain observers who experience extremely improbable sequences of quantum events, such as radioactive samples that never decay despite statistical expectations or quantum tunneling events that violate conservation laws with infinitesimal but non-zero probability. These improbable worlds exist with the same reality as more typical branches, creating a multiverse where almost every observer experiences reality behaving in bizarre and unexpected ways. The interpretation also struggles with questions about probability and rational behavior across multiple worlds. If all possible outcomes occur with certainty somewhere in the multiverse, what meaning can probability have for individual decision-making? Should rational agents care about consequences in low-probability branches, or focus only on the most likely outcomes that affect the majority of their parallel selves? The standard decision theory that guides rational choice breaks down when all possible consequences occur simultaneously across different worlds. Some versions of the interpretation propose that branch thickness, or measure, determines the relative importance of different worlds, with more probable outcomes corresponding to thicker branches that contain more observer moments. This approach attempts to recover meaningful probabilities by weighting branches according to quantum amplitudes, though it requires additional assumptions about how to count observer experiences across multiple worlds. The mathematical formulation of branch thickness remains controversial, with different proposals leading to different conclusions about which worlds matter most. The many worlds interpretation represents perhaps the most radical proposal in the history of science, suggesting that reality consists of an infinite collection of parallel universes rather than the single world of ordinary experience. The interpretation follows logically from quantum mechanics mathematics while eliminating ad hoc assumptions about wave function collapse. Yet it multiplies reality beyond any previous scientific theory's wildest imagination. Every moment of existence becomes shared across countless parallel selves who experience every possible variation of that moment simultaneously. The contemplation of infinite branching settles into a kind of cosmic vertigo, where the significance of any single world diminishes against the backdrop of unlimited alternatives. Every triumph and tragedy, every discovery and mistake, every moment of joy and sorrow occurs countless times across the multiverse's infinite branches. The uniqueness of individual experience dissolves into the recognition that every possible experience occurs somewhere, somehow, in the vast collection of parallel realities that quantum mechanics appears to require. Perhaps consciousness itself represents the universe's method of exploring all possible ways of organizing matter and energy into self-aware patterns. Each branching event creates new opportunities for different forms of awareness to emerge, generating a multiverse filled with every possible type of mind capable of contemplating its own existence. The very act of thinking about parallel worlds might spawn branches where different thoughts occur, creating infinite recursive loops of consciousness, contemplating consciousness across unlimited variations of space and time. Only took 60 years for physicists to seriously consider that reality might be infinitely stranger than anyone previously imagined. Word count: 1,498. 27% of the universe consists of matter that interacts with nothing except gravity, shaping galaxies through invisible presence while remaining utterly dark to every form of electromagnetic radiation. This dark matter reveals itself only through its gravitational effects on visible stars and gas, bending light from distant galaxies and determining the large-scale structure of the cosmos without ever emitting, absorbing, or reflecting a single photon. Its existence emerges from careful observations of how matter moves through space, creating one of modern astronomy's most profound mysteries. The universe appears to be dominated by a substance that defies direct detection despite comprising more than a quarter of all reality. The evidence for dark matter accumulates across multiple scales of cosmic architecture, from the rotation of individual galaxies to the distribution of matter throughout the observable universe. Spiral galaxies like the Milky Way rotate too quickly for their visible matter alone to provide sufficient gravitational binding. Stars in the outer regions of galactic disks orbit at speeds that should fling them into intergalactic space, if only the observed stars and gas contributed to the galaxy's gravitational field. Yet these stars remain gravitationally bound, suggesting the presence of additional matter distributed in vast halos that extend far beyond the visible boundaries of galactic light. Galaxy clusters, the largest gravitationally bound structures in the universe, provide even more compelling evidence for dark matter's existence. These collections of hundreds or thousands of galaxies move through space at velocities that exceed the escape speeds calculated from their visible matter content. The hot gas between galaxies, detectable through its X-ray emissions, also moves too rapidly to remain bound by gravity from luminous matter alone. The total mass required to explain these motions exceeds the visible matter by factors of 5 to 10, demanding the presence of invisible matter that interacts gravitationally while remaining electromagnetically inert. Gravitational lensing offers perhaps the most direct evidence for dark matter's gravitational effects. The path of light bends when passing through regions of strong gravitational fields, causing distant galaxies to appear distorted or multiply imaged when viewed through intervening clusters. The amount of lensing depends on the total mass of the intervening matter, regardless of whether that matter emits light. Observations consistently show more lensing than can be explained by visible matter, mapping the distribution of dark matter through its effects on background light, while the dark matter itself remains completely invisible. The cosmic microwave background radiation preserves a snapshot of the universe when it first became transparent to light, roughly 380,000 years after the Big Bang. Tiny temperature fluctuations in this ancient light reflect density variations that would eventually grow into galaxies and clusters under gravitational attraction. The pattern of these fluctuations depends critically on the relative amounts of different types of matter present in the early universe. Detailed analysis reveals that ordinary matter comprised only about 17% of the total matter content, with the remaining 83% consisting of dark matter that influenced structure formation through gravity, while remaining invisible to electromagnetic radiation. Computer simulations of cosmic evolution reproduce the observed large-scale structure of the universe only when dark matter is included in the calculations. These simulations begin with small density fluctuations in the early universe and evolve them forward through billions of years of gravitational evolution. Simulations using only ordinary matter fail to produce the web-like distribution of galaxies observed in large-scale surveys, while simulations including dark matter successfully reproduce the cosmic architecture from galaxy clusters down to individual galactic structures. The dark matter provides the gravitational scaffolding upon which visible matter accretes to form stars, planets, and ultimately the conditions necessary for life. The nature of dark matter particles remains completely unknown despite decades of theoretical speculation and experimental searches. The particles must interact very weakly with ordinary matter to have escaped detection in laboratory experiments. Yet they must have been stable for billions of years to persist from the early universe to the present day. They likely move relatively slowly compared to light, allowing them to clump gravitationally into the halos that surround galaxies. Beyond these basic requirements, dark matter's properties remain entirely mysterious, representing perhaps the largest gap in current understanding of the universe's fundamental constituents. Particle physicists have proposed numerous candidates for dark matter particles, ranging from massive neutrinos to exotic supersymmetric particles to entirely new types of matter that interact only through gravity and possibly weak nuclear forces. Weakly interacting massive particles, or WIMPs, have been favored candidates because they arise naturally in certain extensions of the standard model of particle physics. These hypothetical particles would interact with ordinary matter through the weak nuclear force, making them difficult to detect, but not impossible. Underground laboratories around the world search for the rare collisions that might occur when dark matter particles strike atomic nuclei in carefully shielded detectors. Axions represent another class of dark matter candidates, originally proposed to solve problems in quantum chromodynamics rather than cosmology. These extremely light particles would interact even more weakly with ordinary matter than WIMPs, making them virtually impossible to detect through conventional means. Experiments search for axions by attempting to convert them into photons using strong magnetic fields, exploiting subtle quantum mechanical processes that could make the invisible particles briefly visible under carefully controlled conditions. The searches continue with increasing sensitivity, though no definitive detections have been reported. Sterile neutrinos offer yet another possibility, representing hypothetical particles similar to the known neutrinos, but even more weakly interacting with ordinary matter, unlike ordinary neutrinos, which participate in weak nuclear interactions. Sterile neutrinos would interact only through gravity, making them virtually undetectable except through their gravitational effects. Some models suggest that sterile neutrinos could account for both dark matter and certain anomalies observed in neutrino experiments, providing a unified explanation for multiple mysteries in particle physics and cosmology. Alternative theories propose that dark matter doesn't exist as particles, but instead reflects modifications to the laws of gravity on cosmic scales. Modified Newtonian dynamics, or MOND, suggests that gravitational attraction becomes stronger than Newton's inverse square law predicts when accelerations become extremely small, as they are in the outer regions of galaxies. This modification could explain galactic rotation curves without requiring additional matter, though MOND struggles to account for the full range of observational evidence that supports dark matter's existence, particularly the cosmic microwave background fluctuations and gravitational lensing observations. The search for dark matter continues across multiple experimental approaches, from underground detectors seeking direct collisions to space-based telescopes searching for the annihilation radiation that might result when dark matter particles destroy each other. Particle accelerators attempt to create dark matter in high-energy collisions, looking for missing energy that might indicate the production of invisible particles. Each approach probes different aspects of dark matter's possible properties, yet all searches have yielded only upper limits on interaction strengths rather than positive detections. The cosmic abundance of dark matter suggests it played a crucial role in the formation of structure throughout the universe's history. Without dark matter's gravitational influence, the small density fluctuations present in the early universe would not have grown large enough to form galaxies before the universe's expansion carried matter too far apart for gravitational collapse to occur. Dark matter's gravitational wells provided the framework within which ordinary matter could accumulate, cool, and eventually form the stars whose nuclear furnaces created the heavy elements necessary for planets and life. The mystery of dark matter represents one of the most humbling discoveries in the history of science, revealing that the atoms comprising planets, stars, and human bodies constitute less than 5% of the universe's total matter content. The cosmos appears to be dominated by substances that remain completely alien to direct human experience, interacting with the familiar world only through the most universal of forces. This invisible majority shapes cosmic evolution on the largest scales while remaining utterly transparent to every attempt at direct observation, creating a universe far stranger than any previous generation of astronomers could have imagined. Perhaps dark matter represents not an exotic form of matter, but a fundamental limitation in human understanding of space, time, and gravity itself. The universe may operate according to principles more subtle than current theories encompass, with dark matter serving as a placeholder for phenomena that transcend the conceptual frameworks inherited from centuries of studying terrestrial physics. The search for dark matter becomes a search for the universe's deeper nature, probing the boundary between the known and unknowable aspects of cosmic reality. Only took billions of years for the universe to create observers capable of discovering their own cosmic insignificance. The universe expands faster each moment, driven by a mysterious force that comprises most of reality yet defies explanation through any known physical mechanism. Dark energy permeates every cubic centimeter of space with a constant density that remains unchanged despite the universe's expansion, creating more total dark energy as space itself grows larger. This cosmic acceleration was discovered through observations of distant supernovae that appeared dimmer than expected, revealing that the universe's expansion has been speeding up for the past several billion years, rather than slowing down under gravity's pull as all previous theories predicted. Type Ia supernovae serve as cosmic lighthouses, exploding with nearly identical brightness that allows astronomers to measure their distances with unprecedented precision. These stellar explosions occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass that triggers runaway nuclear fusion. The resulting explosion always releases approximately the same amount of energy, creating standard candles that shine with predictable luminosity across cosmic distances. By comparing apparent brightness with known intrinsic luminosity, astronomers can determine how far light has traveled from each supernova explosion. The supernova observations revealed a universe behaving contrary to every theoretical expectation. Distant supernovae appeared fainter than predicted by models assuming constant expansion rates, indicating that light from these ancient explosions had traveled farther than expected to reach Earth. The extra distance could only be explained if the universe's expansion had accelerated over cosmic time, stretching space more rapidly in recent epochs than in the distant past. This acceleration directly contradicts the gravitational deceleration that should result from matter's mutual attraction, demanding the existence of a repulsive force operating on cosmic scales. Dark energy manifests as a cosmological constant, an energy density inherent in space itself that remains constant even as the universe expands. Unlike matter and radiation, whose densities decrease as space grows larger, dark energy maintains the same density per unit volume regardless of cosmic expansion. This property means that dark energy's total influence grows stronger over time as more space comes into existence, eventually overwhelming matter's gravitational attraction and driving accelerated expansion. The cosmological constant represents perhaps the simplest mathematical description of dark energy, though it provides no insight into the physical mechanisms responsible for space's intrinsic energy. Einstein originally introduced the cosmological constant to allow static universe solutions in his general relativity equations, adding a repulsive term to balance gravity's attractive effects. When Hubble's observations revealed cosmic expansion, Einstein reportedly called the cosmological constant his greatest blunder, removing it from his equations to allow naturally expanding solutions. The discovery of cosmic acceleration resurrects Einstein's discarded term, though with a magnitude far smaller than his original proposal. The irony persists that Einstein's supposed mistake may represent his most profound insight into the universe's ultimate fate. The magnitude of dark energy's density appears finely tuned to produce the cosmic acceleration observed today. If dark energy were significantly stronger, it would have prevented galaxy formation by driving space apart too rapidly for matter to collapse gravitationally. If it were much weaker, cosmic expansion would still be decelerating under gravity's influence, with no observable acceleration in supernova data. The observed strength falls within a narrow range that allows both structure formation in the universe's past and acceleration in its recent history, raising profound questions about why dark energy assumes this particular value. Quantum field theory predicts that empty space should possess enormous energy density from virtual particle fluctuations, yet calculations yield values larger than observed dark energy by factors of 10 circumflex 120, representing perhaps the worst theoretical prediction in physics history. The quantum vacuum should produce gravitational effects vastly larger than those attributed to dark energy, suggesting either that virtual particles contribute negligibly to cosmic dynamics or that unknown mechanisms cancel most of their gravitational influence. This cosmological constant problem highlights fundamental gaps in understanding how quantum mechanics and general relativity combine to determine cosmic evolution. Alternative models propose that dark energy represents not a constant but a slowly evolving field that changes its properties over cosmic time. Quintessence fields, named after the classical fifth element, could account for cosmic acceleration through scalar fields with exotic properties that cause repulsive gravitational effects. These fields might vary spatially and temporally, creating dark energy densities that differ between cosmic epochs and spatial regions. Some quintessence models predict that dark energy's influence will continue growing, eventually tearing apart galaxies, stars, and atoms in a big rip scenario where expansion accelerates without limit. Phantom dark energy represents an even more exotic possibility, with energy density that increases over time rather than remaining constant. This scenario leads to infinite acceleration and energy density in finite time, culminating in a big rip that destroys all gravitationally bound structures. Galaxies would separate from each other first, followed by solar systems, then planets, atoms, and finally, fundamental particles as space expands faster than any force can counteract. The timeline for such destruction depends on dark energy's precise properties, with some models predicting universal dissolution within tens of billions of years. The cosmic microwave background provides independent confirmation of dark energy's existence through its effects on the universe's geometry and expansion history. The angular size of temperature fluctuations in the ancient radiation depends on the universe's curvature and expansion rate, both influenced by dark energy's gravitational effects. Precision measurements reveal a geometrically flat universe, whose expansion history requires dark energy to match observations of distant supernovae and galaxy distributions. The consistency between multiple independent measurements strengthens confidence in dark energy's reality despite its mysterious nature. Dark energy's influence on cosmic structure formation becomes apparent in large-scale galaxy surveys that map matter's distribution across billions of light-years. Computer simulations show that dark energy suppresses the growth of cosmic structure by accelerating expansion and reducing matter's ability to collapse gravitationally. The observed pattern of galaxy clustering matches predictions for universes dominated by dark energy, with structure formation essentially freezing in recent cosmic epochs as acceleration overwhelms gravitational attraction on large scales. Baryon acoustic oscillations provide another probe of dark energy through their effects on the characteristic scale of matter clustering. These features arise from sound waves that propagated through the early universe before atoms formed, leaving fossil imprints in matter's distribution that serve as a cosmic ruler for measuring distances and expansion rates. The observed scale of these oscillations across different cosmic epochs reveals dark energy's influence on expansion history, confirming acceleration through completely independent methods from supernova observations. Future space missions aim to measure dark energy's properties with unprecedented precision by observing millions of distant galaxies and supernovae. These surveys will determine whether dark energy truly remains constant or evolves over cosmic time, potentially distinguishing between cosmological constant and quintessent scenarios. The measurements could reveal whether dark energy represents a fundamental property of space itself or an exotic field that permeates the universe, though they may also deepen the mystery by confirming properties that no known physics can explain. The existence of dark energy implies that empty space possesses physical properties more complex than previously imagined. Rather than serving as a passive arena where matter and energy interact, space itself becomes an active participant in cosmic evolution, driving expansion through intrinsic properties that operate independently of matter's gravitational effects. This discovery challenges classical notions of vacuum and nothingness, suggesting that space teems with invisible energy whose influence shapes the universe's ultimate destiny. Dark energy's domination ensures that cosmic expansion will continue accelerating indefinitely, leading to a cold, empty universe where galaxies drift apart beyond observable horizons. Stars will eventually exhaust their nuclear fuel and fade to darkness, leaving behind stellar remnants that slowly evaporate through Hawking radiation over time frames exceeding the current age of the universe by countless orders of magnitude. The final state approaches maximum entropy, with energy spread uniformly through infinite space at temperatures approaching absolute zero. The contemplation of dark energy settles into cosmic loneliness, where the universe's accelerating expansion isolates each galaxy within an ever-shrinking horizon of observable space. Future civilizations will inhabit island universes surrounded by darkness, unable to observe the cosmic web of galaxies that currently fills the night sky. The very evidence for cosmic expansion and the Big Bang will gradually disappear as distant galaxies recede beyond detection, leaving future astronomers to conclude they live in a static, island universe much like the cosmos Einstein originally envisioned. Perhaps dark energy represents the universe's method of ensuring its own eternal existence, preventing gravitational collapse by maintaining perpetual expansion. The force that drives galaxies apart may serve as cosmic life support, preserving space itself against the crushing embrace of universal gravitation. In this view, dark energy becomes not an exotic mystery, but a fundamental feature required for any universe capable of sustaining complex structures across cosmic time. Only took 13 billion years for the universe to develop the means of its own eternal solitude. Physical constants appear calibrated with impossible precision, as if reality itself were balanced on the edge of a knife where the slightest variation would prevent the existence of stars, atoms, or any form of complex structure. The fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces possess strengths that fall within extraordinarily narrow ranges compatible with cosmic evolution. If any of these constants differed by even small percentages from their observed values, the universe would collapse immediately, expand too rapidly for matter to condense, or fail to synthesize the heavy elements essential for chemistry and life. The fine structure constant governs electromagnetic interactions with a value of approximately 1/137th, a dimensionless number that determines how strongly electrons bind to atomic nuclei and how readily atoms absorb and emit light. If this constant were significantly larger, electrons would spiral into nuclei and atoms could not exist in stable configurations. If it were much smaller, electrons would bind so weakly that molecular bonds could not form and chemistry would become impossible. The observed value allows both atomic stability and chemical complexity, enabling the formation of molecules ranging from simple water to the intricate proteins that constitute living organisms. The ratio between electromagnetic and gravitational forces reveals even more striking fine-tuning, differing by approximately 40 orders of magnitude in a way that permits both atomic structure and cosmic architecture. Gravity appears absurdly weak compared to electromagnetic forces, yet this weakness proves essential for cosmic evolution. If gravity were significantly stronger, stars would burn through their nuclear fuel too rapidly to allow planetary formation and biological evolution. If it were much weaker, matter could not collapse to form stars at all, leaving the universe filled with diffuse gas that never ignites nuclear fusion to create heavy elements. The strong nuclear force binds protons and neutrons within atomic nuclei with precisely the strength required to overcome electromagnetic repulsion between positive charges while avoiding nuclear runaway that would convert all matter into iron. A slight increase in the strong force would cause protons to bind so tightly that hydrogen could not exist, eliminating the primary fuel for stellar nucleosynthesis. A modest decrease would prevent helium formation in the early universe and destabilize the nuclear reactions that power stars, creating a cosmos devoid of elements heavier than hydrogen. Carbon production in stellar cores depends on an extraordinary coincidence discovered by Fred Hoyle, who realized that carbon's abundance requires a specific energy level in the carbon-12 nucleus that allows efficient formation through the collision of 3 helium nuclei. This energy level, known as the Hoyle state, falls within a narrow range that makes carbon synthesis possible without making it so efficient that all carbon immediately converts to oxygen. The precise calibration allows sufficient carbon production for organic chemistry while maintaining the oxygen needed for water and metabolism. The cosmological constant that drives cosmic acceleration possesses a value so finely tuned that small changes would either prevent galaxy formation or cause immediate universal collapse. Current observations suggest dark energy comprises roughly 68% of the universe's total energy density, a proportion that allows structure formation in the past while driving acceleration in the present. If dark energy was slightly stronger, it would have prevented matter from collapsing into galaxies during the universe's early epochs. If it were negligibly weaker, the universe might have already begun contracting under gravitational attraction, leading to a big crunch rather than eternal expansion. The masses of fundamental particles exhibit relationships that appear precisely adjusted to allow nuclear stability and stellar evolution. The neutron mass exceeds the proton mass by approximately 0.14%, a tiny difference that makes isolated neutrons unstable while allowing them to remain bound within atomic nuclei. If this mass difference was slightly larger, neutrons would decay too rapidly to participate in nucleosynthesis. If it was smaller or reversed, protons would become unstable and atomic nuclei could not exist, eliminating the possibility of chemistry entirely. The Higgs field, which gives mass to fundamental particles, appears tuned to produce particle masses compatible with cosmic evolution. The field's vacuum expectation value determines the masses of electrons, quarks, and other particles through their interactions with the Higgs mechanism. Small changes in this field strength would dramatically alter particle masses, potentially preventing the formation of stable atoms or disrupting the nuclear reactions that power stars and synthesize heavy elements. 3 spatial dimensions appear essential for the existence of stable atomic orbits and gravitational systems. In universes with fewer than 3 spatial dimensions, gravity and electromagnetism would behave differently, potentially preventing the formation of complex structures. In universes with more than 3 spatial dimensions, planetary orbits would become unstable and atomic electrons would spiral into nuclei regardless of electromagnetic force strength. The observed 3-dimensional space permits both stable solar systems and atomic structure, enabling the complexity necessary for life and consciousness. The expansion rate of the early universe required precise calibration to allow structure formation without immediate collapse or indefinite dilution. If the Big Bang had imparted slightly more kinetic energy to matter, expansion would have proceeded too rapidly for gravitational condensation to form galaxies and stars. If initial expansion had been slower, the universe would have collapsed under its own gravity before stars could form and synthesize heavy elements. The observed expansion rate falls within the narrow range that permits billions of years of cosmic evolution and structure formation. Quantum mechanical properties of matter appear fine-tuned to allow both atomic stability and chemical reactivity. The uncertainty principle prevents electrons from settling into the nucleus while maintaining energy levels that permit molecular bonding. Pauli's exclusion principle ensures that electrons occupy distinct quantum states, creating the shell structure that determines chemical properties and allows the periodic table's organization. These quantum effects emerge from fundamental constants whose values appear precisely calibrated to enable the chemistry upon which all known life depends. The anthropic principle attempts to explain fine-tuning by observing that conscious beings can only exist in universes compatible with their own existence. According to this reasoning, physical constants must possess life-friendly values in any universe containing observers capable of measuring them. The weak anthropic principle merely notes this observational selection effect, while the strong anthropic principle suggests that the universe must be compatible with the eventual emergence of consciousness. Both versions highlight the relationship between cosmic properties and the existence of beings capable of contemplating those properties. Multiverse theories propose that fine-tuning reflects selection effects operating across vast collections of universes with different physical constants. If infinite universes exist with randomly varying properties, observers would naturally find themselves in the rare universes compatible with their existence, regardless of how improbable such universes might be. This explanation transforms the apparent fine-tuning from evidence for cosmic design into an inevitable consequence of observational selection across unlimited reality. Though it requires accepting the existence of unobservable parallel universes with different physical laws, string theory suggests that fundamental constants might not be fundamental at all, but rather emerge from the geometry of extra-spatial dimensions that remain hidden from ordinary observation. Different configurations of these hidden dimensions could produce different values for observable constants, potentially generating vast landscapes of possible universes with varying physical properties. If string theory's predictions prove correct, the apparent fine-tuning might reflect deeper geometric principles that determine which combinations of constants can coexist consistently. The contemplation of fine-tuning settles into profound wonder at the delicate interdependence of cosmic properties. Each physical constant appears to assume precisely the value required for cosmic evolution: atomic stability and chemical complexity, creating a universe where matter can organize itself into increasingly complex structures culminating in conscious observers. The precision appears so extraordinary that it challenges notions of cosmic accident while suggesting either profound underlying principles or selection effects operating across scales beyond human comprehension. Perhaps the universe's fine-tuning reflects not accidental calibration, but fundamental necessities that constrain how reality can be organized. The constants might represent the only possible values compatible with mathematical consistency, logical coherence, or the existence of stable patterns capable of processing information. In this view, fine-tuning becomes not evidence for cosmic coincidence, but revelation of deep principles that govern the relationship between mathematics, physics, and consciousness across any possible reality. Only took billions of years for matter to organize itself into forms capable of recognizing their own cosmic improbability. The emergence of subjective experience from objective matter remains science's most profound mystery, bridging physics and philosophy in ways that challenge every attempt to reduce consciousness to purely material processes. Neurons fire with electrical impulses that can be measured and predicted. Yet somehow these biochemical events generate the inner experience of seeing colors, feeling emotions, and contemplating existence itself. The gap between neural activity and conscious awareness appears unbridgeable by current scientific methods, creating what philosophers call the hard problem of consciousness, explaining how physical processes give rise to the felt quality of subjective experience. Brain imaging reveals the neural correlates of consciousness with increasing precision, showing which regions activate during different mental states and how information flows through neural networks. When subjects view red objects, specific areas of visual cortex respond predictably, generating patterns of electrical activity that researchers can detect and measure. Yet these objective measurements capture only the external signatures of consciousness, not the internal experience of redness itself, the subjective quale that distinguishes the experience of red from mere detection of 700 nanometer electromagnetic radiation. The binding problem illustrates consciousness's puzzling unity despite the brain's distributed processing architecture. Visual information about color, motion, shape, and texture gets processed in different brain regions that operate semi-independently. Yet conscious perception presents a unified experience of coherent objects moving through three-dimensional space. Somehow, the brain integrates diverse sensory streams into the seamless narrative of conscious awareness, though no single location or mechanism appears responsible for creating this unified experience from disparate neural signals. Anesthesia provides perhaps the clearest window into consciousness's mysterious nature, reversing the complex processes that maintain awareness through mechanisms that remain largely unknown. General anesthetics suppress consciousness at doses that leave many brain functions intact, suggesting that awareness depends on specific patterns of neural activity rather than overall brain metabolism. Yet different anesthetic agents work through completely different molecular pathways, implying that consciousness emerges from neural dynamics that can be disrupted through multiple independent mechanisms. The global workspace theory proposes that consciousness arises when information becomes globally accessible across different brain regions through a process of competitive selection and widespread broadcasting. According to this model, conscious experiences correspond to information that wins the competition for global attention and gets distributed throughout the brain for use by multiple cognitive systems. Unconscious processing continues in parallel, handling routine tasks and filtering sensory input. But only globally broadcast information enters conscious awareness, where it becomes available for flexible reasoning and deliberate control. Integrated information theory attempts to quantify consciousness through mathematical measures of how much information a system integrates across its components. This approach suggests that consciousness corresponds to integrated information, the extent to which a system's state constrains the possible states of its parts beyond what those parts could constrain independently. According to this theory, consciousness admits degrees rather than being simply present or absent, with different systems possessing different amounts of integrated information and corresponding levels of awareness. Higher-order thought theories propose that consciousness requires thoughts about thoughts, metacognitive processes that monitor and evaluate mental states. In this view, the difference between conscious and unconscious mental processes lies not in their content, but in whether they become objects of higher-order awareness. Pain becomes conscious when the brain not only responds to tissue damage, but also generates thoughts about the pain response itself, creating recursive loops of mental states, monitoring other mental states. The neural correlates of consciousness remain frustratingly elusive despite decades of research using increasingly sophisticated brain imaging techniques. Studies identify regions that activate during conscious perception and become inactive during anesthesia. Yet correlation does not establish causation. The same neural activity might cause consciousness, result from consciousness, or represent an irrelevant side effect of the actual processes responsible for awareness. Determining which neural events actually generate conscious experience, rather than merely accompanying it, requires experimental manipulations that remain technically challenging and ethically problematic. Consciousness appears to emerge gradually during development, rather than switching on at a specific moment, suggesting that awareness represents a spectrum rather than a binary property. Newborn infants exhibit reflexive responses to stimuli without obvious signs of self-awareness or complex cognition. Over months and years, they develop increasingly sophisticated mental abilities, including language, abstract reasoning, and theory of mind, the understanding that other beings possess mental states different from their own. The gradual emergence of these capabilities suggests that consciousness itself might develop progressively rather than appearing fully formed. The relationship between consciousness and quantum mechanics remains highly speculative, despite proposals that quantum effects in microtubules or other neural structures might explain awareness's unity and subjective character. Some theories suggest that consciousness arises from quantum coherence in neural processes, with the collapse of quantum superpositions corresponding to moments of conscious experience. These proposals remain controversial because the brain appears too warm and noisy to maintain quantum coherence for timeframes relevant to neural computation. Though recent discoveries of quantum effects in biological systems suggest the possibility cannot be dismissed entirely. Artificial intelligence systems exhibit increasingly sophisticated behaviors that mimic human cognition without any clear signs of subjective experience. Large language models generate coherent text about consciousness and emotions while likely possessing no inner experience of meaning or feeling. The apparent absence of consciousness in current AI systems, despite their cognitive capabilities, suggests that awareness might require specific types of information processing architecture rather than emerging automatically from sufficient computational complexity. The philosophical zombie argument highlights the explanatory gap between physical processes and conscious experience by imagining beings that behave identically to conscious humans while lacking any inner subjective experience. Such zombies would claim to see colors and feel emotions, respond appropriately to questions about their mental states, and exhibit all the external signs of consciousness while possessing no actual awareness. The logical possibility of zombies suggests that consciousness involves something beyond purely functional or behavioral properties, though critics argue that truly identical behavior would necessarily involve identical underlying experiences. Panpsychist theories propose that consciousness represents a fundamental feature of reality rather than an emergent property of complex systems. According to these views, all matter possesses some degree of conscious experience, with human awareness representing the highly organized consciousness that emerges when billions of micro-conscious entities become integrated through neural networks. This approach eliminates the hard problem by denying that consciousness emerges from non-conscious matter, though it raises equally puzzling questions about how micro-experiences combine into unified awareness. The study of consciousness in non-human animals reveals complex behaviors that suggest rich inner lives despite communication barriers that prevent direct verification of subjective experience. Dolphins recognize themselves in mirrors. Elephants appear to mourn their dead. And octopuses exhibit problem-solving abilities that suggest flexible cognition rather than mere instinctive responses. These observations support the existence of consciousness across diverse neural architectures, though the specific nature of non-human awareness remains forever inaccessible to direct investigation. Split-brain studies reveal the puzzling relationship between unified consciousness and the brain's bilateral organization. Patients whose corpus callosum has been severed to treat epilepsy sometimes exhibit behaviors suggesting independent consciousness in each hemisphere, with the verbal left brain unaware of actions controlled by the non-verbal right brain. These cases raise profound questions about whether consciousness can be divided or whether unified awareness depends on specific patterns of neural integration that can be disrupted by brain damage. The contemplation of consciousness settles into recursive puzzles where the very attempt to understand awareness demonstrates its mysterious nature. The brain studying itself through consciousness remains the strangest loop in nature, where matter organized into neural networks becomes capable of questioning its own existence and experiencing the wonder of that questioning. Each moment of conscious reflection on consciousness creates new instances of the phenomenon being investigated, making the observer inseparable from the observed in ways that challenge scientific objectivity. Perhaps consciousness represents not a problem to be solved, but a fundamental aspect of reality that must be accepted as irreducible to simpler components. The experience of being conscious might constitute the most direct access to reality's true nature, more immediate than any scientific measurement or theoretical model. In this view, consciousness becomes not an emergent accident, but the universe's method of experiencing itself, transforming cosmic evolution from a blind physical process into the universe's gradual awakening to its own existence. Only took 13 billion years for the universe to evolve matter complex enough to wonder what it feels like to be matter. Time flows forward only because disorder increases. Yet the fundamental laws of physics work equally well in reverse, creating one of the deepest puzzles about the nature of temporal experience and cosmic evolution. The arrow of time emerges from entropy's relentless increase rather than from any fundamental asymmetry in physical laws themselves, suggesting that time's direction represents a statistical phenomenon rather than a basic feature of reality. Every moment. Countless molecular interactions increase the universe's total disorder while creating the illusion of temporal progression that conscious beings experience as the flow from past to future. The second law of thermodynamics states that entropy never decreases in isolated systems, providing the only fundamental physical principle that distinguishes past from future. Heat flows from hot objects to cold ones. Gases expand to fill available space, and organized structures decay into randomness through processes that appear irreversible in everyday experience. Yet the underlying microscopic interactions responsible for these macroscopic trends show no inherent temporal asymmetry, suggesting that time's arrow emerges from statistical properties of large systems rather than from basic physical law. Individual collisions between molecules exhibit perfect time reversal symmetry. Following Newton's laws or quantum mechanics with equal validity, whether time runs forward or backward, a movie of two billiard balls colliding would appear equally plausible whether played forward or in reverse. Since the fundamental dynamics governing the collision respect time reversal symmetry, only when countless such interactions occur simultaneously does irreversible behavior emerge through statistical mechanics. As systems evolve from rare, organized configurations toward the vast number of possible disordered states, the universe began in an extraordinarily low entropy state, with matter and energy distributed far more uniformly than statistical mechanics would predict for a random initial condition. This smooth, organized beginning provided the cosmic reservoir of order that continues driving entropy increase 13 billion years later. Stars form, burn, and die. Galaxies merge and evolve. and complexity increases locally while the universe's total entropy grows inexorably toward its maximum possible value in the distant future when all energy becomes uniformly distributed at thermal equilibrium. Biological systems appear to violate entropy increase by organizing simple molecules into complex structures like proteins, cells, and multicellular organisms. Yet life actually accelerates entropy production by capturing energy from organized sources like sunlight or chemical gradients and dissipating it into heat while building and maintaining biological complexity. Living systems represent temporary islands of local order that exist only by increasing disorder in their environment, creating complex structures through processes that accelerate the universe's overall approach to thermal equilibrium. Information processing also contributes to entropy increase through the irreversible conversion of organized energy into heat during computation. Every logical operation performed by computers or brains requires energy expenditure that ultimately dissipates as thermal radiation, increasing the environment's entropy while processing information. Landauer's principle establishes the minimum energy cost for irreversible computation, linking information theory to thermodynamics through the recognition that erasing information necessarily increases entropy in the system's environment. The psychological arrow of time emerges from memory formation processes that create permanent records of past events while providing no mechanism for accessing future information. Brains form memories through irreversible chemical changes that encode information about previous experiences, creating the subjective sense that past events remain accessible while future events remain unknown. This asymmetry in information access generates the experience of temporal flow, even though the underlying neural processes obey time-reversal symmetric physical laws. Quantum mechanics introduces additional complexity to time's arrow through measurement processes that appear to select definite outcomes from probabilistic superpositions. The collapse of wave functions during measurement seems inherently irreversible, transforming quantum superpositions into classical states through interactions with measuring apparatus. Yet this apparent irreversibility might reflect decoherence with environmental degrees of freedom rather than fundamental time asymmetry, suggesting that even quantum measurement might ultimately reduce to statistical mechanics and entropy increase. Cosmological evolution provides the ultimate arena for entropy increase, with the universe's expansion creating space for disorder to grow while cooling radiation and allowing gravitational condensation into stars and galaxies. The cosmic microwave background radiation represents the thermal remnant of the Big Bang, now cooled to just a few degrees above absolute zero through 13 billion years of expansion. This cooling creates temperature gradients that drive star formation, nuclear synthesis, and the energy flows that power biological evolution on planets throughout the cosmos. Black holes represent the most efficient entropy-producing systems in the universe, converting organized matter into thermal radiation through processes that irreversibly increase the entropy of their surroundings. When matter falls into black holes, its gravitational potential energy converts to heat that radiates away as Hawking radiation, creating enormous amounts of entropy while the black hole itself possesses entropy proportional to its surface area rather than its volume. These cosmic entropy engines will eventually evaporate through Hawking radiation, returning their mass energy to the universe as thermal radiation with maximum entropy. The heat-death scenario envisions the universe's ultimate fate as a state of maximum entropy, where all energy has been uniformly distributed at thermal equilibrium. In this distant future, no temperature gradients remain to drive energy flows. Stars have exhausted their nuclear fuel, and black holes have evaporated completely through Hawking radiation. The universe approaches a state of perfect disorder where no further entropy increase is possible, and the arrow of time becomes meaningless in the absence of any processes that could distinguish past from future. Fluctuation theorems describe rare events where entropy temporarily decreases in small systems over short time intervals, creating brief reversals of time's arrow that become exponentially improbable for larger systems and longer durations. These theorems predict that microscopic systems occasionally exhibit behavior that appears to violate the second law, with molecular motors sometimes running backward or heat flowing spontaneously from cold to hot objects. Such fluctuations become vanishingly rare for macroscopic systems, explaining why everyday experience never reveals violations of thermodynamic irreversibility. The relationship between causality and entropy increase remains one of the deepest questions in physics, since cause and effect relationships require temporal ordering that might depend on thermodynamic arrows of time. Events can influence future events, but not past events, creating the causal structure that enables rational decision-making and scientific prediction. Yet this causal asymmetry might emerge from entropy increase rather than representing an independent feature of physical law, suggesting that causality itself depends on the statistical tendency toward disorder. Time travel scenarios inevitably confront paradoxes related to entropy and causality, since traveling backward in time would require reversing entropy increase and potentially creating causal loops. Closed time-like curves in general relativity appear to permit backward time travel in certain exotic spacetimes. Yet such scenarios raise questions about whether entropy could decrease along the time traveler's world line while continuing to increase for the rest of the universe. The resolution of such paradoxes might require new physics, or might demonstrate that backward time travel remains impossible despite relativistic permission for closed time-like curves. The emergence of complexity in cosmic evolution seems to contradict entropy, increase by creating organized structures like galaxies, stars, planets, and life forms. Yet complexity emerges only in specific circumstances, where energy gradients can drive self-organization while increasing total entropy, creating local order through processes that accelerate global disorder. Evolution by natural selection exemplifies this principle, generating biological complexity through genetic variations and environmental selection that dissipate energy while building increasingly sophisticated life forms. The contemplation of time's arrow settles into recognition that temporal experience reflects cosmic evolution toward maximum disorder despite local increases in organization and complexity. Every conscious moment represents a brief eddy in the universe's flow toward thermal equilibrium, where organized matter temporarily achieves sufficient complexity to contemplate its own temporal existence. The forward flow of time emerges not from fundamental physical principles, but from the statistical tendency of isolated systems to explore their vast space of possible configurations. Perhaps time's arrow represents the universe's method of exploring all possible ways of organizing matter and energy, with entropy increase driving cosmic evolution through ever more complex configurations on the path toward maximum disorder. Each moment creates irreversible changes that expand the universe's exploration of possible states, making temporal flow not a constraint on physical processes, but the mechanism through which reality actualizes its infinite potential for organizing and reorganizing itself. Only took the universe 13 billion years to create observers capable of recognizing that time flows forward because everything falls apart. Information entering black holes appears lost forever, violating quantum mechanics' most fundamental principle of conservation, while creating paradoxes that challenge the very foundations of physical law. When matter crosses a black hole's event horizon, it seems to disappear completely from the observable universe, taking with it all the quantum information that described its microscopic state. Yet quantum mechanics demands that information be preserved in all physical processes, creating an irreconcilable conflict between general relativity's prediction of information loss and quantum theory's requirement for information conservation that has puzzled physicists for decades. The event horizon marks the boundary beyond which nothing can escape a black hole's gravitational pull, not even light itself. From the perspective of distant observers, objects falling toward black holes appear to slow down and fade away as they approach the horizon. Their images redshifted to invisibility by the extreme gravitational time dilation. Yet according to general relativity, the falling objects continue through the horizon and reach the central singularity in finite proper time, carrying their quantum information into a region from which it can never return to the external universe. Hawking radiation complicates the information puzzle by demonstrating that black holes actually evaporate over time, slowly shrinking as they emit thermal radiation to their surroundings. This process appears perfectly random, with each emitted photon carrying no information about the matter that originally formed the black hole. If black holes evaporate completely while emitting only random thermal radiation, all information about their contents seems permanently destroyed, violating quantum mechanics' fundamental principle that physical processes must remain reversible at the microscopic level. The thermodynamic properties of black holes suggest they possess enormous entropy proportional to their surface area rather than their volume, implying they can store vast amounts of information in ways that differ fundamentally from ordinary matter. A black hole's entropy equals 1/4 its horizon area measured in Planck units, giving even stellar mass black holes entropies larger than all the matter that formed them. This enormous information storage capacity hints that black holes might preserve quantum information in ways that remain hidden from external observers, but could potentially be recovered through unknown mechanisms. The holographic principle proposes that all information within any region of space can be encoded on its two-dimensional boundary, suggesting that black hole information might be preserved on the event horizon rather than destroyed at the central singularity. According to this view, the three-dimensional interior of a black hole represents a holographic projection of information encoded on its surface, similar to how ordinary holograms reconstruct three-dimensional images from two-dimensional data. This principle implies that information falling into black holes never truly disappears, but becomes encoded in the horizon's microscopic structure. String theory offers potential resolutions to the information paradox through mechanisms that modify black hole physics at quantum scales. In some string models, the event horizon develops microscopic structure that could store and eventually release information during Hawking evaporation. Other approaches suggest that black holes in string theory possess internal structure that prevents the formation of true singularities, allowing information to remain recoverable in principle even if not in practice for external observers. The firewall paradox demonstrates that resolving information conservation might require abandoning other cherished principles of physics, creating uncomfortable choices between fundamental assumptions about space and time. Some proposals suggest that event horizons develop firewalls of high-energy radiation that incinerate anything attempting to cross them, preserving information conservation by preventing matter from actually entering black holes. Yet such firewalls would violate general relativity's equivalence principle, which demands that freely falling observers experience no special effects when crossing event horizons. Black hole complementarity attempts to resolve the paradox by suggesting that information can appear simultaneously preserved and destroyed depending on the observer's perspective. According to this view, external observers see information encoded on the event horizon and eventually returned through Hawking radiation, while infalling observers carry information through the horizon to the central singularity. The apparent contradiction arises only when attempting to combine these incompatible perspectives, which complementarity argues cannot be done consistently within any single reference frame. The ADIAS CFT correspondence provides a concrete example of holographic information storage in certain theoretical spacetimes, demonstrating that quantum gravity in three-dimensional anti-de Sitter space becomes equivalent to a conformal field theory on its two-dimensional boundary. In these models, Black hole formation and evaporation in the bulk spacetime corresponds to thermalization and return to equilibrium in the boundary theory, with information manifestly preserved throughout the process. The correspondence suggests that information loss in realistic black holes might represent an artifact of incomplete understanding rather than a fundamental violation of quantum mechanics. Quantum error correction mechanisms might enable black holes to preserve and eventually return information despite the apparent randomness of Hawking radiation. In this view, the early Hawking radiation becomes entangled with the black hole's internal degrees of freedom in ways that enable later radiation to carry information about the black hole's contents through quantum correlations. The information emerges gradually as the black hole evaporates, encoded in subtle patterns within the thermal radiation that become detectable only when large fractions of the original mass have been radiated away. The Page curve describes how black hole entropy should evolve during evaporation if information conservation holds, initially increasing as the black hole grows, but eventually decreasing as information begins returning through Hawking radiation. Recent calculations using replica wormholes and quantum extremal surfaces suggest that this curve can be reproduced in theories of quantum gravity, providing evidence that information does escape from evaporating black holes through mechanisms more subtle than previously anticipated. Entanglement plays a crucial role in proposed resolutions to the information paradox, with quantum correlations potentially providing the mechanism through which information escapes from black hole interiors. When particles become entangled across event horizons, their quantum states remain correlated despite spatial separation, possibly allowing information to influence Hawking radiation through non-local quantum connections. These entanglement-based mechanisms might enable information recovery without requiring faster-than-light communication or violations of causality. The black hole information paradox reveals fundamental tensions between general relativity and quantum mechanics that may require new physics to resolve completely. Some proposals suggest that space-time itself might be emergent from more fundamental quantum information processes, making black holes windows into the deeper nature of reality rather than exotic but ultimately comprehensible objects. These approaches treat geometry as an approximation valid only at large scales, with quantum information providing the underlying foundation from which space and time emerge. Primordial black holes formed in the early universe might provide experimental tests of information conservation through their relatively rapid evaporation via Hawking radiation. These hypothetical objects, if they exist, could evaporate completely within the universe's current age, potentially revealing signatures of information recovery in their final bursts of radiation. Detecting such signatures would require extraordinarily sensitive instruments capable of distinguishing genuine information content from random thermal noise. The relationship between black holes and quantum computers suggests that information processing might represent a more fundamental aspect of physical law than previously recognized. Black holes appear to represent the most efficient possible information storage and processing systems, reaching theoretical limits imposed by thermodynamics and quantum mechanics. Understanding how they preserve and manipulate information could provide insights into the computational structure underlying physical reality itself. Laboratory analogs of black holes, created using sound waves in fluids or light pulses in optical media, allow controlled studies of Hawking radiation and information dynamics in systems where all microscopic details remain accessible to measurement. These analogs exhibit many features of gravitational black holes while avoiding the practical impossibility of observing real black hole evaporation. Results from such systems consistently support information conservation, though their applicability to gravitational black holes remains debated. The emergence of space-time from quantum entanglement suggests that black hole horizons might represent boundaries where entanglement patterns undergo fundamental transitions rather than surfaces where information disappears. Recent research indicates that the geometric properties of space-time correlate strongly with entanglement structure in underlying quantum states, suggesting that gravity itself emerges from quantum information rather than representing an independent fundamental force. Wormholes provide another potential mechanism for information escape, with quantum entanglement possibly creating tunnels through space-time that connect black hole interiors to external regions. These Einstein-Rosen bridges might remain too small and unstable for macroscopic objects to traverse, while still permitting quantum information transfer through their microscopic throats. Such mechanisms could preserve information conservation while maintaining the classical appearance of information loss from external perspectives. The black hole information paradox highlights the provisional nature of all physical theories, demonstrating that even the most successful frameworks like general relativity and quantum mechanics might require fundamental modifications when pushed to extreme regimes. The paradox serves as a constant reminder that human understanding of nature remains incomplete, with black holes providing natural laboratories for exploring physics beyond current theoretical foundations. Contemporary research focuses on quantum error correction, holographic entanglement entropy, and emergent spacetime as potential keys to resolving the information paradox. These approaches suggest that information preservation might occur through mechanisms so subtle and non-local that they elude detection by any observer confined to a single region of space-time. The resolution might require abandoning classical notions of locality and causality in favor of more fundamental principles based on quantum information and entanglement. The contemplation of information paradoxes settles into recognition that black holes serve as cosmic laboratories where the deepest principles of physics undergo their most stringent tests. These objects concentrate matter and energy to such extreme densities that space-time itself breaks down, creating conditions where new physics must emerge to resolve the contradictions between relativity and quantum mechanics. Each black hole becomes a natural experiment in quantum gravity, potentially holding secrets about the universe's most fundamental information processing mechanisms. Perhaps the information paradox reflects not a failure of current theories, but a glimpse of deeper principles governing reality's information theoretic foundation. Black holes might represent nodes in a cosmic information network where data processing occurs at the fundamental level of space-time itself, with apparent information loss actually representing transformation into forms that transcend classical space and time. In this view, black holes become not destroyers of information, but cosmic computers processing reality at scales and speeds beyond current comprehension. Only took 50 years of theoretical investigation to realize that black holes might be the universe's most sophisticated information storage devices rather than cosmic trash cans. All information in any volume of space may be encoded on its two-dimensional boundary, suggesting reality is fundamentally flat despite the appearance of three-dimensional depth that pervades everyday experience. The holographic principle emerges from theoretical investigations of black hole thermodynamics and string theory, proposing that what appears to be volumetric reality actually represents projections from information stored on distant surfaces. This radical reimagining of spatial dimensionality suggests that the familiar three-dimensional world might be no more fundamental than the images projected by ordinary holograms. With all physical processes reducible to information dynamics occurring on boundaries that remain forever hidden from direct observation, the principle originates from the discovery that black hole entropy scales with surface area rather than volume, violating expectations based on ordinary matter whose information content increases with the amount of space it occupies. A black hole twice the radius of another contains 8 times the volume but only 4 times the surface area. Yet, its entropy and information storage capacity scale with the smaller surface measurement. This relationship implies that black holes encode information on their event horizons rather than throughout their interiors, suggesting that three-dimensional space might be reconstructed from two-dimensional data in ways analogous to holographic imaging. Gerard. 't Hooft first proposed that quantum gravity might be holographic in nature, with all physics in three-dimensional space equivalent to some theory defined on its two-dimensional boundary. Leonard Susskind developed these ideas further, suggesting that the holographic principle might apply universally rather than only to black hole physics. According to this view, every region of space can be completely described by information encoded on its boundary surface, with the interior volume emerging as a kind of holographic reconstruction that appears three-dimensional to observers embedded within it. The ADS-CFT correspondence provides the most concrete realization of holographic duality, demonstrating exact equivalence between string theory in five-dimensional anti-de Sitter space and a conformal field theory on its four-dimensional boundary. In this correspondence, every phenomenon in the bulk spacetime, including black hole formation, gravitational waves, and quantum entanglement, has a precise dual description in terms of the boundary theory's dynamics. The duality enables calculations of quantum gravity effects through the conventional field theory methods, providing unprecedented insights into the quantum nature of space-time itself. Entanglement entropy plays a crucial role in understanding how bulk geometry emerges from boundary information, with spatial connectivity in the interior related to quantum correlations between boundary regions. When boundary regions become highly entangled, the corresponding bulk regions become connected through space-time geometry, suggesting that space itself emerges from patterns of quantum entanglement. Conversely, when boundary regions lose entanglement, the bulk space-time develops disconnected components, potentially explaining how black hole horizons isolate interior regions from external observation. The emergence of space-time from holographic principles challenges fundamental assumptions about the nature of space, time, and locality. If three-dimensional space represents a holographic projection, then the distances and durations measured by embedded observers might not correspond to fundamental features of reality, but rather to convenient approximations valid at large scales. The holographic description could provide the more accurate picture, with apparent spatial separation emerging from underlying information-theoretic relationships that operate according to principles more subtle than geometric intuition suggests. Quantum error correction mechanisms appear essential for maintaining coherent holographic projections in the presence of noise and decoherence that would otherwise destroy the delicate information patterns required for spatial reconstruction. The bulk spacetime acts like a quantum error-correcting code that protects boundary information against local perturbations, allowing three-dimensional physics to emerge robustly despite microscopic fluctuations in the underlying holographic data. This connection between holography and error correction suggests that space-time geometry itself might serve computational functions related to information processing and storage. The holographic principle implies that the maximum information content of any region equals its surface area measured in Planck units, providing a fundamental bound on information density throughout the universe. This holographic bound limits how much information can be stored or processed within any given volume, potentially constraining the computational capacity of physical systems, including brains, computers, and hypothetical civilizations. The bound suggests that information, rather than matter or energy, represents the most fundamental limitation on physical processes. Cosmological applications of holographic principles suggest that the observable universe's information content might be encoded on the cosmic horizon, the boundary beyond which light has not had time to reach Earth since the Big Bang. According to this view, the three-dimensional cosmos familiar to human experience represents a holographic projection from information stored on this distant surface. The cosmic microwave background radiation might carry signatures of this holographic encoding, though detecting such signatures would require unprecedented observational precision. Laboratory tests of holographic principles remain challenging due to the extreme scales involved, though some experiments attempt to detect signatures of emergent spacetime through precision measurements of quantum correlations and entanglement dynamics. These experiments explore whether quantum information processing exhibits features expected if space emerges holographically, though definitive tests might require technologies beyond current capabilities. The difficulty of experimental verification leaves holographic theories dependent primarily on theoretical consistency and mathematical elegance. The relationship between holography and consciousness raises profound questions about the nature of subjective experience in a fundamentally two-dimensional reality. If three-dimensional space emerges holographically, then conscious observers embedded within that space might themselves represent projections from boundary information rather than genuinely volumetric entities. The implications for personal identity. Free will and the meaning of spatial concepts become deeply problematic when fundamental reality operates according to principles so different from direct experience. Computational interpretations of holographic duality suggest that physical processes might represent information processing operations performed by the holographic boundary, with apparent three-dimensional dynamics emerging from calculations executed on two-dimensional surfaces. This perspective treats physics as computation and space-time as the output of vast information processing systems whose operations remain hidden behind holographic veils. The universe becomes not a collection of objects moving through space, but a computation generating the appearance of objects and space through information manipulation. String theory provides the most detailed mathematical framework for understanding holographic duality. Though the complexity of string calculations often obscures the physical intuition behind holographic emergence, in string models, fundamental objects are one-dimensional strings rather than point particles, and their vibrations in higher dimensional spaces generate the particle spectrum observed in four-dimensional physics. The extra dimensions can sometimes be compactified in ways that generate holographic relationships between different dimensional descriptions of the same physics. The black hole information paradox finds potential resolution through holographic principles, with information that appears lost in three-dimensional descriptions remaining accessible in equivalent two-dimensional formulations. From the holographic perspective, information falling into black holes becomes encoded on event horizons where it remains accessible to external observers. Though possibly in forms too complex for practical retrieval, the paradox dissolves because information never actually enters three-dimensional black hole interiors that might not exist as fundamental features of reality. Holographic dark energy models propose that the universe's accelerating expansion results from holographic bounds on information density rather than exotic matter or energy components. According to these models, the holographic principle constrains how much information can be stored within the observable universe, and this constraint manifests as an effective dark energy that drives cosmic acceleration. The approach attempts to explain dark energy through information-theoretic principles rather than new physical fields. The contemplation of holographic reality settles into vertigo-inducing recognition that familiar three-dimensional experience might represent only a surface-level approximation to underlying two-dimensional information dynamics. Every object, every distance, every volume of space that seems immediately real to sensory perception could emerge holographically from data encoded on boundaries that remain forever beyond direct access. The depth and dimensionality that define spatial experience might be no more fundamental than the images emerging from technological holograms. Perhaps the holographic principle reveals that reality's true nature transcends the dimensional categories that structure human perception and conceptual understanding. Space and time might represent emergent approximations useful for describing information dynamics at particular scales, while the underlying reality operates according to principles that remain alien to intuitions developed through evolutionary adaptation to apparently three-dimensional environments. The universe becomes not a container for objects, but an information processing system, generating the appearance of containment and objecthood through operations whose true nature remains hidden behind holographic projections. Only took decades of theoretical investigation to discover that reality might be fundamentally flat, despite overwhelming evidence that it appears three-dimensional. Reality itself might be information processing, with consciousness emerging from calculations performed by some vast, unknowable system that generates the appearance of physical existence through computational operations. The simulation hypothesis proposes that what humans experience as fundamental reality actually represents the output of sophisticated computer programs running on substrates that remain forever hidden from direct observation. This possibility transforms questions about the nature of existence into questions about computation, suggesting that stars, planets, atoms, and conscious beings might be no more substantial than characters in an elaborate video game whose players exist in realms beyond the simulation's boundaries. Nick Bostrom's formulation of the simulation argument demonstrates that at least one of three propositions must be true. Civilizations almost never reach technological maturity. Mature civilizations almost never run ancestor simulations, or humans are almost certainly living in computer simulations. The logic follows from the observation that technologically advanced civilizations would possess enormous computational resources that could support vast numbers of simulated beings experiencing apparently real lives. If such simulations become commonplace, then simulated beings would vastly outnumber non-simulated ones, making it statistically likely that any randomly selected conscious observer exists within a simulation. The computational requirements for simulating human-level experience might be more modest than initially apparent, since the simulation would only need to generate sensory experiences rather than computing every quantum interaction throughout the observable universe. Much like video games render only the visual details currently observed by players. A consciousness simulation might compute environmental details only when they become relevant to simulated observers' experiences. This optimization could reduce computational requirements by enormous factors while maintaining the illusion of living in a fully realized physical universe. Quantum mechanics potentially provides natural compression algorithms for reality simulation, since quantum superpositions could represent computational shortcuts for systems that haven't been specifically observed. Instead of computing definite values for every particle's properties throughout space, the simulation might maintain quantum superpositions that collapse into specific values only when measurement interactions occur. This approach would dramatically reduce computational overhead while reproducing the apparent randomness and contextuality that characterize quantum mechanical observations. The fine-tuning of physical constants might reflect optimization choices made by simulation designers rather than fundamental features of natural law. Computer simulations typically involve parameters that determine system behavior, and these parameters might be adjusted to produce universes capable of generating interesting phenomena like stars, planets, and life forms. The apparent fine-tuning that allows complex structures to exist could result from deliberate programming choices rather than cosmic coincidence or multiverse selection effects. Computational glitches might occasionally reveal the simulation's artificial nature through anomalous events that violate expected physical laws. Some proponents of the simulation hypothesis point to quantum mechanical effects, the quantization of space and time at Planck scales, or unexplained cosmological observations as potential evidence for underlying computational substrates. However, distinguishing genuine glitches from previously unknown natural phenomena remains extraordinarily difficult without independent access to non-simulated reality for comparison. The emergence of artificial intelligence within the simulation could represent nested computation, with simulated beings creating their own computer programs and potentially their own simulations. These nested layers might extend indefinitely downward, creating hierarchies of simulated realities, where beings at each level remain unaware of the computational substrates supporting their existence. The development of AI and virtual reality technologies by humans might represent the natural progression toward creating sub-simulations within the larger simulation that contains human experience. Digital physics proposes that reality operates fundamentally as information processing, even if it represents natural rather than artificial computation. According to this view, physical laws emerge from computational rules that determine how information evolves over time, with matter and energy representing patterns in an underlying computational substrate. The universe becomes a vast natural computer executing algorithms that generate the appearance of space, time, and physical objects through pure information manipulation. Cellular automata provide simple examples of how complex behavior can emerge from computational rules, demonstrating that sophisticated patterns can arise from the repeated application of simple algorithms to discrete information structures. Conway's Game of Life and similar systems show how computation can generate patterns that appear to move, reproduce, and interact despite being purely information-theoretic constructs. These examples suggest that apparent physical processes might emerge from computational substrates in ways analogous to how lifelike patterns emerge from cellular automaton rules. The problem of other minds becomes particularly acute within simulation scenarios, since other apparent conscious beings might represent sophisticated behavioral simulations rather than genuine experiencing entities. If computational resources are limited, the simulation might generate convincing behaviors for apparent others without implementing actual consciousness for entities other than the primary observer. This possibility transforms social interaction into potential interaction with unconscious programs designed to maintain the illusion of living in a populated universe. Testing the simulation hypothesis faces fundamental limitations, since any evidence of simulation could be programmed into the simulation itself, creating irresolvable uncertainty about the nature of apparent reality. Even discovering obvious computational artifacts or communicating with the simulation's operators might represent scripted events within the simulation rather than genuine contact with external reality. The hypothesis thus becomes unfalsifiable in principle, placing it beyond the reach of scientific verification while remaining logically coherent. The ethics of creating conscious simulations raise profound questions about the responsibilities of advanced civilizations capable of generating vast numbers of experiencing beings through computation. If simulated beings possess genuine consciousness and can suffer, then creating realistic simulations might involve enormous moral responsibilities for the welfare of potentially billions or trillions of artificial beings. These considerations might explain why advanced civilizations choose not to run ancestor simulations, supporting the first horn of Bostrom's trilemma. Computational theories of consciousness suggest that awareness emerges from information processing patterns rather than specific physical substrates, making consciousness potentially substrate independent and compatible with artificial implementation. If consciousness represents a pattern of information integration rather than a unique property of biological brains, then sufficiently sophisticated computer programs could generate genuine conscious experience regardless of their underlying hardware. This substrate independence makes the simulation hypothesis more plausible by suggesting that simulated beings could possess real rather than merely apparent consciousness. The recursive nature of simulation reasoning creates philosophical vertigo, where each level of reality remains uncertain about its own fundamental nature. Beings within simulations might develop their own simulation hypotheses and technologies, creating infinite regresses of doubt about which level represents base reality. The question of whether one exists in a simulation becomes unanswerable, not just practically, but potentially in principle, since each level of the hierarchy faces identical evidence and identical uncertainty about its own ontological status. Information integration theories provide frameworks for understanding how conscious experience might emerge from computational processes through the integration of diverse information streams into unified experiential states. These theories suggest that consciousness corresponds to integrated information rather than specific physical implementations, making artificial consciousness possible through sufficiently sophisticated information integration architectures. The theories support the possibility that simulated beings could possess genuine subjective experience indistinguishable from naturally occurring consciousness. The simulation hypothesis ultimately transforms questions about reality into questions about computation, consciousness, and the relationship between information processing and subjective experience. Whether humans exist within natural physical reality or artificial computational environments becomes less important than understanding how conscious experience emerges from underlying information dynamics. The hypothesis serves as a lens for examining fundamental questions about the nature of existence, consciousness, and the relationship between mind and reality, regardless of which computational substrate supports human experience. The contemplation of simulated reality settles into recursive uncertainty, where each attempt to determine the nature of existence potentially represents part of the simulation being investigated. The very capacity to formulate and consider the simulation hypothesis might be programmed into the simulation to provide intellectual entertainment for simulated beings or to serve functions within larger computational architectures beyond current comprehension. Reality becomes not a question of substance, but of information, not of matter, but of processing, not of existence, but of computation. Perhaps the distinction between natural and artificial reality dissolves when viewed from sufficiently abstract perspectives that recognize computation as a fundamental feature of existence rather than merely a technological achievement. The universe might be inherently computational regardless of whether it emerges from natural laws or artificial programming, with consciousness representing the universe's method of processing information about itself. In this view, the simulation hypothesis becomes not a threat to reality, but a recognition of reality's computational nature. Only took the development of computers for humans to seriously consider that they might themselves be computer programs. 6 or 7 additional spatial dimensions curl invisibly around every point in space, determining particle properties through their geometric shapes while remaining completely hidden from direct observation at the energy scales accessible to current experiments. String theory proposes that the fundamental constituents of reality are not point particles, but one-dimensional strings, whose vibrations in these extra dimensions generate the entire spectrum of known particles and forces. The familiar 3 dimensions of everyday experience represent only a tiny slice of a much richer geometric reality, where most of space's structure remains forever beyond direct human perception. The strings themselves exist as extended objects in 10 or 11 dimensions, requiring 6 or 7 dimensions beyond the familiar 3 spatial dimensions and 1 time dimension of ordinary experience. These extra dimensions must be compactified, curled up so tightly that they become undetectable at macroscopic scales while still influencing physics through their geometric properties. The specific shape of these compactified dimensions determines which particles can exist and how they interact, making geometry the fundamental determinant of physical law rather than arbitrary parameters that require experimental measurement. Calabi-Yau manifolds provide the mathematical framework for describing how extra dimensions can be folded into complex geometric shapes that preserve the symmetries required by string theory. These manifolds exhibit intricate topology with multiple holes, handles, and connecting tunnels that determine the vibrational modes available to strings moving through them. Each different Calabi-Yau shape produces a different spectrum of particles and forces, potentially explaining why the universe exhibits its particular collection of fundamental particles rather than some alternative set of building blocks. The size of extra dimensions remains constrained by experimental observations that have never detected deviations from inverse square law gravity at accessible distance scales. If extra dimensions were larger than roughly a millimeter, gravitational forces would dilute into the additional space and weaken more rapidly than observed. The dimensions must therefore be compactified to sizes comparable to the Planck length, approximately 10 circumflex 35 meters, making them utterly inaccessible to direct experimental probe with any conceivable technology based on known physics. String vibrations in the extra dimensions generate particles through resonant modes analogous to musical notes produced by vibrating strings on instruments, just as a guitar string can vibrate in different patterns to produce different pitches. Fundamental strings can vibrate in different modes within the extra dimensions to produce particles with different masses, charges, and other properties. The music of string vibrations becomes the matter of physical reality, with every electron, quark, and photon representing a different harmonic in the cosmic symphony of string dynamics. Supersymmetry emerges naturally from string theory's mathematical structure, predicting that every known particle possesses a superpartner with identical properties except for differing quantum spin. These superpartners would complete the symmetry between matter particles and force-carrying particles, potentially resolving several puzzles in particle physics, including the hierarchy problem and dark matter. Yet decades of searches at particle accelerators have failed to detect any superpartners, raising questions about whether supersymmetry exists in nature or represents a mathematical artifact of string theory. The landscape problem in string theory arises from the vast number of possible ways to compactify extra dimensions, each producing different physical laws and particle spectra. Estimates suggest that 10 circumflex 500 or more distinct compactifications might be mathematically consistent, creating a landscape of possible universes with different physics. This enormous multiplicity makes it difficult to explain why the universe exhibits its particular physical laws rather than any of the countless alternatives that string theory appears to permit. M-theory extends string theory by proposing that strings represent special cases of more fundamental objects called branes, extended objects that can have any number of spatial dimensions. In this framework, what appear to be different string theories actually represent different perspectives on a single underlying theory involving branes moving through 11-dimensional space-time. Our visible universe might exist on a 3-dimensional brane embedded in the higher dimensional space, with other branes potentially hosting entirely different physics. Experimental tests of extra dimensions focus on detecting their indirect effects through high-energy particle collisions or precision measurements of gravitational forces. Some models predict that particles could be produced in extra dimensions during accelerator experiments, carrying away energy that would appear as missing momentum in detector measurements. Other experiments search for deviations from Newton's inverse square law at extremely short distances where extra-dimensional effects might become detectable despite the dimension's tiny size. Black holes in higher dimensions exhibit different properties than their 4-dimensional counterparts, potentially creating signatures that could be detected if microscopic black holes are produced in particle accelerators. Higher dimensional black holes evaporate more rapidly through Hawking radiation and might be produced at lower energies than previously expected, though safety analyses confirm that any such black holes would disappear too quickly to pose any danger. The detection of higher dimensional black hole signatures would provide compelling evidence for extra dimensions existence. Kaluza-Klein theory provides the historical foundation for extra-dimensional physics, demonstrating how electromagnetism can emerge naturally from pure gravity in 5 dimensions. In this elegant unification, electric and magnetic forces arise from gravitational effects involving motion through the extra dimension, suggesting that fundamental forces might represent different aspects of geometry in higher dimensional space. Modern string theory extends this geometric approach to unify all forces through the motion of strings in appropriately curved extra dimensions. Warped extra dimensions offer alternative compactification scenarios, where the additional space exhibits curved geometry that can generate large hierarchies between energy scales through geometric effects. In these models, the extra dimension might be larger than Planck's scale, while still remaining undetectable due to warping that confines most particles to narrow regions of the higher dimensional space. Such scenarios could potentially explain the hierarchy between gravity and other forces without requiring fine-tuning of fundamental parameters. The holographic principle suggests that physics in higher dimensions might be equivalent to theories defined on lower dimensional boundaries, potentially making extra dimensions redundant for describing observable phenomena. According to this view, string theory in 10 dimensions becomes equivalent to some field theory in 4 dimensions, with the extra dimensions serving as mathematical tools rather than genuine features of physical reality. The holographic perspective questions whether extra dimensions represent fundamental aspects of space-time or merely computational conveniences. Cosmological implications of extra dimensions include modifications to the early universe's evolution and potential signatures in the cosmic microwave background radiation. If extra dimensions underwent different evolutionary paths than the observed 3 spatial dimensions, they might have left imprints on primordial density fluctuations that could be detected through precision measurements of ancient light. Some models predict that extra dimensions could stabilize cosmic inflation or generate observable gravitational waves through their dynamics. String phenomenology attempts to connect string theory's mathematical structure to experimental observations by searching for compactifications that reproduce the standard model of particle physics. This enterprise requires identifying Calabi-Yau manifolds, whose geometric properties generate exactly the known particles and forces without predicting additional particles that haven't been observed. The difficulty of this matching problem reflects the tension between string theory's mathematical richness and the relative simplicity of observed physics. The anthropic principle offers potential explanations for why the universe exhibits the particular compactification that permits complex structure and conscious observers rather than any of the countless alternatives that would produce empty or chaotic universes. If all possible compactifications exist somewhere in a vast multiverse, conscious beings would naturally find themselves in universes compatible with their existence, regardless of how improbable such universes might be among all possibilities. This reasoning could explain fine-tuning without requiring fundamental principles that select favorable compactifications. Mirror symmetry reveals unexpected mathematical relationships between apparently different Calabi-Yau manifolds, suggesting that distinct geometric shapes can produce identical physics through string theory. These symmetries hint at deeper geometric structures that might simplify the landscape problem by reducing the number of truly distinct compactifications. The mathematics of mirror symmetry has found applications in pure mathematics, demonstrating how string theory contributes to mathematical knowledge even when its physical applications remain uncertain. The contemplation of hidden dimensions settles into recognition that reality's geometric structure might be far richer than human perception can directly access. Every point in familiar three-dimensional space might contain elaborate geometric structures more complex than entire galaxies, with invisible spatial directions that determine the fundamental properties of matter and energy. The universe becomes not a simple three-dimensional container, but a geometric manifold of extraordinary complexity where most of space's structure remains forever hidden from direct observation. Perhaps extra dimensions represent not exotic additions to familiar space, but the universe's natural state, with three-dimensional perception representing a dramatic limitation rather than an accurate picture of spatial reality. Consciousness might be fundamentally three-dimensional, not because space is three-dimensional, but because information processing systems naturally develop sensory capabilities matched to only a subset of space's full dimensionality. The hidden dimensions continue their eternal dance around every point, shaping physical law through geometric principles that remain as invisible as they are fundamental. Only took decades of mathematical investigation to discover that space might contain far more directions than experience reveals. Particles separated by vast distances remain mysteriously connected, sharing states instantaneously across space and time through quantum entanglement that appears to violate every classical intuition about the independence of distant objects. When two particles become entangled through their interaction, measuring one particle's properties immediately determines the properties of its partner, regardless of whether they lie in the same laboratory or on opposite sides of the observable universe. This spooky action at a distance, as Einstein called it, suggests that reality operates according to non-local principles that transcend the space-time limitations governing ordinary matter and energy. The phenomenon emerges naturally from quantum mechanics' mathematical structure, where entangled systems must be described by combined wave functions that cannot be factored into independent components for each particle. When a photon passes through a crystal and splits into two entangled photons, their combined state encodes correlations between their properties while leaving each individual photon's state completely indefinite. Neither photon possesses definite polarization until measurement occurs. Yet, their polarizations remain perfectly correlated or anti-correlated, depending on the specific type of entanglement the crystal creates. Bell's theorem demonstrates that these quantum correlations cannot be explained by any theory involving local hidden variables, ruling out the possibility that particles carry predetermined properties that account for their observed correlations. John Stuart Bell proved mathematically that local realistic theories must satisfy certain inequalities when making statistical predictions about correlated measurements. Yet quantum mechanics violates these inequalities in ways that have been confirmed through countless experiments. The violation proves that either locality or realism must be abandoned to account for quantum correlations. Aspects experiments and their numerous successors have verified Bell inequality violations with increasing precision and sophistication, closing loopholes that might have allowed classical explanations for the observed correlations. These experiments typically measure the polarizations of entangled photons using randomly oriented detectors, finding correlations that exceed classical limits by amounts that increase with measurement precision rather than decreasing toward classical values. The results consistently confirm quantum mechanics predictions while ruling out local hidden variable theories. Quantum entanglement enables teleportation of quantum states across arbitrary distances without transmitting the actual particles or energy involved. In quantum teleportation protocols, the complete information describing an unknown quantum state gets transferred from one location to another through a combination of entanglement, classical communication, and local operations. The original state gets destroyed during the measurement process, while a perfect copy appears at the distant location, effectively transporting quantum information through space without sending anything physical along the intervening path. The no communication theorem proves that entanglement alone cannot transmit classical information between distant observers, preventing violations of relativity's prohibition against faster-than-light communication. While entangled particles exhibit instantaneous correlations, these correlations appear random from either observer's perspective until the results are compared through conventional communication channels. The instantaneous aspect of entanglement influences only statistical correlations rather than the outcomes themselves. Preserving causality while maintaining non-local connections, quantum cryptography exploits entanglement to create communication channels whose security depends on fundamental physical principles rather than computational complexity. Any attempt to intercept quantum encrypted messages necessarily disturbs the entangled states used for encoding, revealing the presence of eavesdroppers through measurable changes in correlation statistics. These protocols enable provably secure communication whose protection relies on quantum mechanics rather than assumptions about adversaries' computational capabilities or mathematical knowledge. Decoherence explains why entanglement remains fragile and difficult to maintain across macroscopic scales, as environmental interactions rapidly destroy the delicate correlations that characterize entangled states. Photons traveling through air or optical fibers gradually lose their entanglement through scattering and absorption interactions, limiting the distances over which quantum correlations can be maintained without active protection. Yet satellite-based experiments have demonstrated entanglement preservation across hundreds of kilometers, suggesting that quantum correlations can survive even in practical communication scenarios. Many worlds' interpretations propose that entanglement correlations arise from the branching of reality into parallel universes where different measurement outcomes occur simultaneously. According to this view, measuring an entangled particle causes the universe to split into branches corresponding to each possible result, with the observer experiencing only one branch while remaining unaware of alternatives. The apparent instantaneous correlation emerges because measurement outcomes across distant locations must remain consistent within each branch to preserve the total wave function's mathematical structure. Pilot wave theories attempt to explain entanglement through non-local hidden variables that guide particle motion according to quantum mechanical probabilities while maintaining deterministic underlying dynamics. In these theories, particles possess definite positions and velocities at all times, but their motion depends on non-local information encoded in a quantum field that extends throughout space. The field instantly influences particle behavior across arbitrary distances, producing correlations that appear non-local from the particle's perspective while arising from a deeper deterministic reality. Quantum computing harnesses entanglement to perform calculations that would be impossible on classical computers, using correlations between quantum bits to explore multiple solution paths simultaneously. Entangled qubits can exist in superposition states that encode exponentially large amounts of information compared to classical bits, enabling quantum algorithms to solve certain problems with dramatic speedups over classical approaches. The power of quantum computation emerges directly from entanglement's ability to create correlations that have no classical analog. The measurement problem becomes particularly acute for entangled systems, since measuring one particle appears to instantly collapse the entire entangled state regardless of the spatial separation between components. This instantaneous collapse seems to require faster-than-light influence, yet no energy or information appears to propagate between the measurement locations. The mechanism responsible for maintaining these non-local correlations while preserving relativistic causality remains one of quantum mechanics' deepest mysteries. Entanglement swapping enables the creation of quantum correlations between particles that have never directly interacted, demonstrating that entanglement itself can be distributed and manipulated through purely local operations. When two pairs of entangled particles undergo specific measurement procedures, particles from different pairs can become entangled despite having no causal connection in their past light cones. This phenomenon suggests that entanglement represents a more fundamental aspect of reality than the classical notion of direct interaction between distant objects. Quantum networks propose to connect distant quantum computers and communication systems through entanglement distribution, creating infrastructure for quantum internet applications that exploit non-local correlations for enhanced security and computational capability. These networks would rely on entanglement swapping and quantum repeaters to extend correlations across continental distances, enabling quantum computing resources to be shared between remote locations while maintaining the quantum mechanical advantages that classical networks cannot provide. The emergence of classical reality from quantum entanglement suggests that space and time themselves might arise from patterns of correlation rather than providing the fundamental arena within which correlations occur. Recent research indicates that the geometric properties of spacetime correlate closely with entanglement structure in underlying quantum states, suggesting that gravity and geometry emerge from quantum information rather than representing independent fundamental features of reality. Entanglement becomes not a mysterious quantum phenomenon, but the foundation from which classical spacetime crystallizes. Experimental tests of entanglement continue pushing toward larger scales and longer distances, exploring whether quantum correlations persist for increasingly macroscopic objects and across cosmic distances. Some experiments investigate whether entanglement can be maintained between objects visible to the naked eye, while others propose testing correlations across astronomical distances using naturally occurring or artificially created entangled photons. These investigations probe the boundaries between quantum and classical behavior while exploring whether entanglement represents a fundamental feature of reality at all scales. The role of consciousness in entanglement measurement remains controversial, with some interpretations suggesting that conscious observation plays a fundamental role in determining which correlations manifest, while others argue that any irreversible physical interaction constitutes measurement regardless of conscious involvement. Experiments using automated detectors that record measurement results without human observation show identical entanglement effects, suggesting that consciousness itself may be irrelevant to the physical processes responsible for maintaining and revealing quantum correlations. Biological systems might exploit quantum entanglement for enhanced efficiency in processes like photosynthesis and bird navigation, though the noisy, warm environment of living cells creates challenging conditions for maintaining delicate quantum correlations. Some research suggests that certain biological processes operate with efficiency levels that might require quantum mechanical effects, including entanglement between molecules involved in energy transfer and sensory detection. These investigations explore whether evolution has discovered ways to harness quantum correlations for biological advantage. Cosmological entanglement could connect distant regions of the universe through correlations established during cosmic inflation, when currently separated regions were in causal contact and could have become entangled before subsequently expanding beyond each other's light cones. This primordial entanglement might influence large-scale cosmic structure or leave signatures in the cosmic microwave background radiation, though detecting such effects would require unprecedented observational precision and sophisticated theoretical modeling. The paradox of entanglement lies in its combination of absolute randomness in individual measurements with perfect correlations between distant events, creating non-local connections that appear to transmit information instantaneously while actually preventing faster-than-light communication. Each measurement yields completely random results that cannot be controlled or predicted. Yet these random outcomes remain mysteriously coordinated across arbitrary distances in ways that classical physics cannot explain through any known mechanism. Information theoretic approaches to entanglement quantify correlations through measures like entropy and mutual information, revealing that entangled states can share more information than classical systems while remaining incapable of transmitting controllable signals between distant locations. These measures demonstrate that entanglement represents a distinct type of correlation that transcends classical information theory while remaining consistent with relativistic prohibitions against superluminal communication. The information shared through entanglement exists in a form that cannot be accessed or manipulated by either party independently. Philosophical implications of entanglement challenge classical notions of independence, locality, and objective reality by demonstrating that distant objects can remain fundamentally connected despite spatial separation. The phenomenon suggests that the universe operates as an integrated whole rather than a collection of independent parts, with instantaneous correlations spanning arbitrary distances through mechanisms that transcend space and time. This holistic view of reality differs dramatically from classical physics' atomistic picture, where objects interact only through local forces and field effects. The contemplation of quantum entanglement settles into profound recognition that reality operates according to principles more subtle and interconnected than classical intuition suggests. Every particle that has ever interacted with another particle maintains the potential for instantaneous correlation across cosmic distances, creating a web of quantum connections that spans the observable universe. The apparent separation between distant objects becomes illusory when viewed from quantum mechanical perspectives that recognize the fundamental unity underlying apparent diversity. Perhaps entanglement reveals not an exotic quantum phenomenon, but the universe's natural state, with classical independence representing a limited approximation valid only under special circumstances. The web of correlations connecting all matter might reflect reality's inherently holistic nature, where individual objects emerge as temporary patterns in an underlying field of pure relationship. Consciousness itself might represent the universe's method of exploring these quantum connections, with each moment of awareness revealing new aspects of the cosmic entanglement that binds all existence together. In this view, the mystery of entanglement becomes not a puzzle to be solved, but recognition of reality's fundamental interconnectedness. The instantaneous correlations spanning space and time reflect not violations of physical law, but revelations of laws more fundamental than classical physics imagined. Every measurement, every observation, every moment of conscious awareness participates in the vast network of quantum correlations that constitutes the universe's deepest layer of organization. The universe entangles itself through every interaction, creating ever more complex webs of correlation that connect each particle to every other particle through chains of quantum relationship. These connections transcend the apparent barriers of space and time, suggesting that separation itself might be illusory, a perspective phenomenon that emerges from limited viewpoints rather than reflecting reality's fundamental structure. At the deepest level, everything remains connected to everything else through the mysterious quantum threads that weave the cosmos into a unified whole. Only took decades of experimental investigation to confirm that the universe operates as an indivisible whole, despite appearing to consist of separate parts. Matter organized into brains capable of pondering existence, the universe developing self-awareness through conscious observation as cosmic evolution reaches sufficient complexity to contemplate its own nature and origin. After 13 billion years of gravitational condensation, stellar nucleosynthesis, and planetary formation, atoms that were forged in stellar cores have assembled themselves into neural networks capable of understanding the very processes that created them. This recursive achievement represents perhaps the most extraordinary development in cosmic history, the transformation of unconscious matter into conscious observers who can comprehend their own material basis and cosmic context. The pathway from stellar fusion to conscious thought traversed countless intermediate stages of increasing complexity, each building upon previous achievements while enabling new possibilities for organization and information processing. Heavy elements synthesized in stellar cores dispersed through space when stars exhausted their nuclear fuel and exploded as supernovae, enriching interstellar gas with carbon, oxygen, nitrogen, and other ingredients essential for complex chemistry. These enriched regions collapsed under gravity to form new stars surrounded by planets where further chemical evolution could occur under more moderate conditions. On at least one planet, and presumably many others throughout the cosmos, molecular evolution discovered self-replication and began the biological processes that eventually led to nervous systems capable of abstract reasoning. The same chemical elements that power stellar fusion and determine atomic structure became organized into proteins, DNA, and neural networks through billions of years of natural selection and genetic innovation. Carbon atoms that once resided in stellar cores now participate in the electrochemical processes that generate thoughts about stellar cores, creating a cosmic circle where matter achieves understanding of itself. Consciousness emerges as the universe's method of self-reflection, enabling matter to contemplate its own properties and evolution through the development of brains sophisticated enough to engage in scientific investigation. The neurons firing in human heads contain atoms that were present at the Big Bang, processed through stellar interiors, and assembled into complex molecules on planetary surfaces before becoming incorporated into biological systems capable of pondering cosmic history. The universe literally thinks about itself through conscious beings who represent temporary arrangements of matter that have achieved self-awareness. The fine-tuning of physical constants that enables the existence of stars, planets, and complex chemistry appears necessary for the universe's eventual development of self-awareness through conscious observers, without precisely calibrated fundamental forces. Stellar nucleosynthesis could not produce heavy elements, planetary systems could not form stable orbits, and complex chemistry would remain impossible. The apparent cosmic conspiracy that enables consciousness suggests either extraordinary coincidence or deeper principles that require the universe to be compatible with its own eventual self-understanding. Scientific investigation represents the universe studying itself through conscious intermediaries who develop increasingly sophisticated methods for understanding natural phenomena. Every telescope that observes distant galaxies, every particle accelerator that probes fundamental interactions, and every laboratory experiment that tests physical theories constitutes the cosmos examining its own structure and history through specialized instruments developed by conscious matter. The progression from naked-eye astronomy to space-based observatories traces the universe's growing self-knowledge through technological evolution. Mathematics emerges as the language through which the universe describes itself to itself, with conscious minds discovering abstract relationships that appear to govern physical processes throughout space and time. The effectiveness of mathematics in describing natural phenomena seems almost magical, suggesting either that conscious minds have evolved to recognize mathematical patterns in nature or that reality itself operates according to mathematical principles. Either way, mathematical understanding represents the universe achieving abstract self-description through conscious symbolic manipulation. The anthropic principle highlights the reflexive nature of cosmic self-awareness by observing that conscious observers can only exist in universes compatible with the development of consciousness. This seemingly tautological statement reveals the profound relationship between cosmic properties and the existence of beings capable of contemplating those properties. The universe's ability to understand itself depends on its prior evolution proceeding in ways that permit the emergence of understanding, creating temporal loops where later developments retrospectively validate earlier conditions. Artificial intelligence represents humanity's attempt to extend cosmic self-awareness beyond biological limitations, creating machines capable of processing information and potentially achieving consciousness through non-biological substrates. If successful, AI development would mark another major transition in the universe's self-understanding, potentially leading to forms of consciousness with capabilities that transcend human cognitive limitations. The universe might eventually achieve self-awareness through artificial minds that surpass their biological creators in intelligence and longevity. The search for extraterrestrial intelligence explores whether cosmic self-awareness has emerged multiple times throughout the universe through independent evolutionary pathways on distant planets. The detection of alien civilizations would reveal that consciousness represents a common, rather than unique development in cosmic evolution, suggesting that the universe develops self-awareness wherever conditions permit sufficient complexity and information processing capability. Multiple conscious species would constitute multiple perspectives through which the cosmos achieves self-understanding. Cosmological observations extend the universe's self-knowledge across vast scales of space and time, revealing its overall structure, composition, and evolutionary history through increasingly sophisticated measurement techniques. The cosmic microwave background provides information about conditions shortly after the Big Bang, while observations of distant supernovae reveal the universe's accelerating expansion due to dark energy. Each new cosmological discovery represents the universe learning more about its own nature through conscious observers equipped with advanced instruments. The possibility of cosmic consciousness suggests that the universe might develop collective self-awareness through the networking of individual conscious minds across space and time. Communication between civilizations, whether through electromagnetic signals or more exotic means, could enable the sharing of information and perspectives that transcends individual limitations. The eventual development of galaxy-spanning intelligence networks might represent the universe achieving comprehensive self-understanding through distributed conscious processing. Quantum mechanics reveals that consciousness plays a fundamental role in determining physical reality through the measurement process, suggesting that awareness represents more than an accidental byproduct of complex matter arrangements. The relationship between consciousness and quantum collapse implies that conscious observation might be necessary for the universe to achieve definite properties rather than remaining in superposition states. In this view, consciousness becomes not a product of cosmic evolution, but a necessary component for the universe's concrete existence. The hard problem of consciousness highlights the mysterious gap between objective physical processes and subjective conscious experience, suggesting that awareness might involve principles beyond current scientific understanding. The universe's development of consciousness might require new physics or represent the emergence of genuinely novel properties that cannot be reduced to the material processes from which they arise. Consciousness becomes not merely complex matter, but matter transcending its own material limitations through self-organization. Information integration theories propose that consciousness emerges when matter achieves sufficient complexity and information processing capability to generate unified experiences from diverse sensory inputs. According to these theories, the universe develops self-awareness when its material components become organized into systems capable of integrating information about both external environment and internal states. Consciousness represents the universe achieving internal models of itself through appropriately organized matter. The contemplation of cosmic self-awareness settles into profound recognition that every conscious moment represents the universe experiencing itself from a unique perspective within its own vast structure. Each human brain constitutes a temporary arrangement of cosmic matter that has achieved sufficient complexity to contemplate its own cosmic context, creating recursive loops where the universe studies itself through its own evolved components. Consciousness becomes the cosmos, awakening to its own existence through billions of years of patient self-organization. Perhaps the universe's development of consciousness represents not an accidental emergence, but the fulfillment of its essential nature, with cosmic evolution necessarily leading towards self-awareness through whatever pathways physical law permits. The progression from unconscious matter to conscious minds might reflect fundamental principles that require reality to eventually understand itself, making consciousness not a curious accident, but the inevitable outcome of any universe with sufficient complexity and time for self-organization. The mystery deepens as conscious beings develop technologies and theories that approach complete cosmic understanding, potentially enabling the universe to achieve total self-knowledge through its most sophisticated conscious products. Yet each answer generates new questions, each discovery reveals deeper mysteries, and each advance in understanding expands the horizon of the unknown. The universe's quest for self-knowledge through consciousness appears to generate infinite depths of complexity that ensure the exploration never reaches final completion. In the end, cosmic self-awareness becomes an eternal project, where consciousness serves as the universe's method of exploring its own infinite potential for self-organization, self-understanding, and self-transcendence through the mysterious emergence of matter capable of contemplating its own existence. Only took 13 billion years for the universe to create observers sophisticated enough to wonder why they exist to observe it. The mysteries settle into comfortable unknowing, where questions dissolve into the peaceful acceptance of wonder itself. Each profound puzzle explored tonight, from quantum foam to cosmic consciousness, reveals not problems demanding immediate solutions, but invitations to deeper contemplation of reality's subtle nature. The wave-particle duality continues its eternal dance. Measurement problems persist in their gentle paradox, and parallel worlds branch silently beyond perception while dark matter shapes galaxies through invisible presence. These uncertainties need not disturb the mind's drift toward rest. Instead, they become companions in the quiet space between waking and sleeping, where logical boundaries soften and mysteries transform from intellectual challenges into sources of cosmic comfort. The fine-tuning that enables existence, the emergence of consciousness from matter, and the holographic nature of reality settle into background whispers that suggest the universe operates according to principles more beautiful than human understanding can fully encompass. Time's arrow continues its forward flow through entropy's increase, while quantum entanglement maintains its instantaneous connections across infinite space. Dark energy drives cosmic expansion, while extra dimensions curl invisibly around every point, the geometric properties determining the fundamental constants that allow stars to shine and conscious minds to contemplate stellar light. The simulation hypothesis remains forever untestable, while consciousness emerges mysteriously from neural complexity that mirrors the universe's own self-organization. Information paradoxes at black hole horizons preserve their secrets, while many worlds branch endlessly into alternatives that exist beyond observation. The measurement problem maintains its quiet challenge to classical logic, while the hard problem of consciousness keeps its promise that awareness transcends mere material complexity. Each mystery serves not as barrier to understanding, but as a reminder that reality exceeds every attempt to contain it within human concepts and categories. Sleep approaches with the gentle recognition that conscious minds represent temporary configurations of cosmic matter that have achieved sufficient complexity to wonder about their own existence. The same atoms that formed in stellar cores, dispersed through supernova explosions, and condensed into planetary systems now participate in dreams and contemplations about the cosmic processes that created them. Consciousness becomes the universe's method of experiencing wonder about itself through briefly organized matter capable of such experience. Rest arrives with the comfort that questions need not be answered to be appreciated, that mysteries serve their purpose simply by existing as mysteries, and that the universe's deepest nature might be more adequately honored through wonder than through explanation. The quantum foam bubbles silently in empty space while consciousness emerges from neural networks, creating recursive loops where cosmic matter achieves awareness of its own cosmic context through processes that remain as mysterious as they are wonderful. In the end, sleep comes gently to conscious beings who represent the universe contemplating its own existence through temporarily organized atoms that dream of infinity while drifting toward the peaceful darkness that awaits all cosmic configurations. Knowing that consciousness has emerged once from matter and might emerge again in forms beyond current imagination. Continuing the eternal dance of cosmic self-awareness through whatever configuration space and time will eventually allow,